esteemed researchers, scholars, and the bright minds gathered here today. We are honored to welcome you to the In Situ Planetary Explorations and International Symposium hosted by Patil International University, Akurdi, Pune. This symposium brings together leading experts from across the global diaspora who are deliberating on the cutting-edge advancements, challenges, and future prospects in planetary explorations, space exploration across Moon, Mars, and beyond. Space exploration has always captivated humanity's imagination, pushing the boundaries of science, engineering, and human ingenuity. In situ planetary exploration, from lunar soil sampling to Martian terrain analysis, provides invaluable data that shape our quest for interplanetary knowledge and future colonization. Today, we have the privilege of learning from some of the most accomplished scientists and engineers in this field. Their insights will not only deepen our understanding, but also inspire the next generation of space explorers. To commence today's proceedings, we are honored to invite Professor Shashi Singh, Vice Chancellor in charge, to deliver the welcome address. Professor Shashi Singh is an eminent scientist of India with 35 years of experience in interdisciplinary research. Her leadership in research continues to inspire many in the scientific community. Let us give her a warm round of applause.
Yeah. Good morning, everybody. I welcome you all to this International Symposium on In Situ Planetary Exploration. And today we have assembled here a lineup of speakers from various space agencies who work in situ explorations and of course various other things. And you must be aware of a lot of things happening in the cosmos, which we are quite, we are in a position now to decipher it out because of this various kinds of activities the researchers take in their labs or across the, what do you say, across the cosmos again I will use, because we are, earlier most of the things were remotely accessed and we were able to understand what is the kind of terrain, what is the atmosphere at various planets or planetary bodies. But we have the explorations in space actually push the boundaries of human capacities and ingenuity basically, and in situ explorations require a little more effort because you have to be, it's almost like comparing yourself, like you have visited a site through your internet sources or by artificial, what do you say, a virtual world, and when you actually go to that space, that feeling is completely different. So you can just imagine that when you're doing a remote examination of a planet or planetary body, the things will be slightly different from what when you actually collect the samples or you send a rover over there, which does a lot of measurement and keeps sending you the data, is actually like touch and feel the things and manage the research here. It gives you a lot of much more wider idea what is happening, how, let's say, if we want to inhabit those places or we have to sort of mine those areas or utilize the resources of other planets, things will be totally different. And to do these kind of things, we really need a lot of knowledge about various fields. It is not only how to send a vehicle across our atmosphere and to other spaces, but actually to reach to those planetary bodies where gravity, atmosphere, temperature, pressure, everything differs, and the kind of material which is required, it's a totally different kind of a challenge. So we need inputs, again an interdisciplinary area where you need inputs from mechanics, you need inputs from computer sciences, you need inputs from information technology and you need inputs from electronics. Everything puts together, and then that's how you are able to do this interdisciplinary kind of exploration. So let's hear from the stalwarts who have gathered here from different space agencies and other things, and also from India. And I welcome you all. You are here. The quest is simple, that we need to understand what's happening in the cosmos and how we can utilize these informations. Thank you.
Thank you, Professor Singh, for setting the tone and vision for this important gathering. It is a true privilege to introduce our first speaker, Professor Bernard Huang, a pioneering figure in international lunar and planetary explorations. Professor Huang is a senior scientist at the European Space Agency and the executive director of International Lunar Exploration Working Group. He has played a central role in Europe's moon mission, including SMART 1, ESA's first mission to the moon, where he served as a chief scientist. His leadership has shaped global lunar strategy and fostered international collaboration towards sustainable moon exploration. What makes his presence especially important for today's symposium is his deep engagement with in situ planetary science, from developing technologies and scientific instruments that operate on other worlds to design analog missions and lunar research bases here on Earth that simulate future human robotics exploration. Professor Huang is also a leading advocate of the moon village concept, a vision for international cooperation in building a sustained lunar presence using in situ resources and technologies. His work bridges science, engineering, policy, and global collaboration. Yes, sir, we can hear you. So please join me in warmly welcoming Professor Bernard Huang as he shares his perspective on the future of in situ planetary explorations.
शेयर करना पड़ेगा.
Excellent. Thank you. The new partners of the European Mars collaboration, the program we started some 15 years ago. That was initially using support from various space agencies, ESA, NASA, and universities and companies. And indeed, we have different pillars in our activities. Some concern data and science with the group. And in particular now, we are applying new tools to analyze data, to merge them, to combine them in a geographical system, but also to use machine learning and AI to analyze. We have been also involved in the development of technology, in particular for instruments. Please stay on the previous slide. Yeah. The first slide, the one we had before.
Yeah, now it is.
The previous slide. The first slide.
Yeah, it is already there.
Okay, so go fast. Yeah. So we have that. We have instruments. We also have looked at how to implement some of these instruments on top of a mission, space mission to fly. We have also access to laboratory and field site where we can demonstrate some of these instruments. More recently, also in the last 15 years, we have done some astronaut simulation in some bases, moon Mars bases, to train how to work and live on the moon. 5 years ago, we also got some funding on the aspect of space entrepreneurship, where we have been also training young startups together with space researchers and us. And in the form of a collaboration with another foundation called Space Renaissance International, we developed also some advocacy, some policy, some humanistic aspect, and some cultural and artistic and societal program. So what about India? The next slide, please. I have the pleasure to visit India. So we can go to the second slide.
Yeah, it is already there. It is already there.
Second slide.
It is already changed. Please go ahead.
Okay, yes, excellent. Yes, and indeed, more than 20 years ago, I did a number of travel to India after we had been flying our mission to the moon, Smart One. We also started a collaboration with some Indian, with ISRO, to contribute to the Chandrayaan-1 mission. And actually, we identified 3 instruments from the ISRO that were put on board Chandrayaan-1. And also in this opportunity, we organized a big in DYPIU, where even President Abdul Kalam and I had the honor and privilege to present him the first result from our Smart launch, which had been flown in 2003. But we had also a series of other events in India. In 2007, we organized the International Astronautical Congress in Rabat, and organized there, for instance, some sessions, some plenary, but also we organized some moon Mars workshop with the space generation, and you can see them in the yellow t-shirt there. More recently, also, I was invited in Ahmedabad, the Physical Version Research Laboratory, where there was an international conference on planetary exploration and habitability and exoplanet, where so we had a great exchange with Indian and international scientists. We also were celebrating Professor Michel Mayor, Nobel Prize in astrophysics, and we had a very good scientific and social moment in India. More recently, that was this week, we were in Delhi for the GLEX Global Exploration Conference that was organized by IF, ISRO, and the Indian Society of Astronautics, and where there were big exchange, great also moment, but as well very good technical presentation where we heard some news about lunar and planetary mission. Next slide shows some work we have done in the area of data analysis, in particular on Mars. As I am co-investigator of an instrument on Mars called the HRST, High Resolution Stereo Camera. And this has unveiled a completely new view of Mars. We discovered some signs of the past history of Mars, vast volume of water flooded on the surface of Mars in the past. And also we found signature of buried glaciers in some areas, even in the tropics, in matter of catastrophic flood. So we could study the effect of the tectonic evolution of the planet. So that was this Mars Express, which has revolutionized our view of Mars. After this, we have started another one called ExoMars program, where we launched, that's the next slide, we launched an orbiter in 2016 that is still in operation, and we are preparing for a rover called Rosalind Franklin that is equipped with the payload package of instruments called PASTA, and that's a goal to search for signs of ancient life, or even present life on the surface of Mars, equipped with a drill that can go down to 2 meters in an area where putative life or advanced biology could have survived the radiation. So that's for our activities in preparation for Mars and data analytics. Next slide shows you the focus on analyzing lunar data. And in particular, so the next slide, please. I was in charge of the first mission to the moon of Europe. That was called the Smart One. Next slide. Thank you. And with this mission, we tested some technologies for traveling in deep space, for spacecraft, but also for miniaturization of instruments. Do you hear me? Next slide.
Yeah, it is a smart one peak of light. Is that
Yeah.
okay? Next change.
Yeah. Yes. Okay. We have the. Okay. Oh, yeah. Hold on. Yeah. Let's say that. So we had then the contribution of our mission, Smart One, where we mapped, in particular, the areas around the pole of the moon. We also identified some areas with more eternal light, and also some areas of permanent shadow that could contain volatiles. But at that time also, we started collaboration with other countries that were developing lunar missions. That includes China with the Chang'e 1 and Japan with the Kaguya Selene, both launched in September 2007. And we contributed to the science of those missions. With India, as I mentioned, we also contributed instruments on board of Chandrayaan-1, so some infrared spectrometer, some energetic neutral instrument, and as well X-ray instrument to map the composition of the moon. There was also on board the MQ from NASA, an hyperspectral imager that had the first proof of polar volatile, hydroxide containing volatiles, so it could be ice, could be also mineral with OH, and a big discovery done by Chandrayaan-1. We also contributed to Chandrayaan-1 from the system point of view, from the ground station, and we also contributed to subsequent mission of the Chandrayaan-1 program. Then, in 2009, there was the launch of the Lunar Reconnaissance Orbiter, LRO, together with L-Cross, that was the probe that impacted the moon in a polar area, and had also another proof of the existence of a subsurface ice of about 5% in the area of Arctic. We can go to the next slide. That's a slide that describes the roadmap for exploration of the moon that we established actually some 30 years ago with ILUX, the International Lunar Exploration Laboratory, and it was created in 1994, and we proposed a phased approach for lunar exploration and utilization and settlement. So starting with robotic reconnaissance exploration with orbiters, then some landers and permanent robotic presence, we call that the robotic village. Then the mission with outpost with a short duration, human stay, and then a phase with a mounted human outpost and a permanent human base with humans and robots. That we call the moon village. And so how can we contribute to some of this journey and roadmap towards a settlement for the benefit of humanity? So first, we have also to do some experiments in the free space. Next slide, we have been involved in a number of experiments on board of platform, so-called exposure facilities, where you can measure organisms or compounds survive in space. So from long duration exposure facilities, we were also having some sample on board of an experiment called Biopan that was flown on board a photon capsule for and in space for 3 weeks. And we had also some experiment on exposed facility on board of the International Space Station, first flown in 2009 and then the second time in 2012. And so we have been involved also in a series of experiments where we exposed various compounds, also living organisms, to see how they survive, they could degrade, and eventually are modified by exposure to space. So that's important aspect. Now, more recently, next slide, we have been involved in developing some payloads for future exploration. Some payloads include some cameras that we had on board previous mission, like the Moon mission, like Mars mission, and for the future. And we are now preparing the exploitation of those cameras, but also we looked at new instruments like spectrometers, reflectance spectrometers, Raman spectrometers, and now high-flash spectral imager that allow to characterize some samples. Actually, here you can see on the top right an image of our laboratory equipment, imager where we can map some samples and we can measure for each point of the sample the spectrum that allows to characterize their composition or even their content in organics or even in living material. So we also develop techniques for analyzing the samples of soil. So that's for institute, and we do that in the lab. We also developed a lander, so-called exogeolab lander, and we described later, this was in the frame of Google United Prize competition, but we tested how we could equip it, not only with instruments, cameras or rovers, but also with a telescope that would be very useful to perform science from the moon, but also that the telescope could monitor the remote operation by astronauts, by rovers at distance from the lander. And as you know, there have been some telescopes that were flown recently to the moon with the Chang'e 3 lunar mission. China had the Ultra telescope, and also more recently, there was some telescope on the Intuitive Machine mission 1, built by ILOA, International Lunar Observatory Association, and we are collaborating with it. So we did also some work on the rovers and also multiple rovers to see how we can perform cooperative. So we built this exogeolab lander. You can see this lander on the moon. So this is the real picture of the lander. But the landscape of the moon, this was created by my students that for my birthday gave me a postcard with our dream telescope and lander on the surface of the moon. We hope to see that. We actually worked for preparation of mission to the moon, our moon, and particularly the icy part of our moon. But we looked how we could adapt this lander if we would want to land on an icy moon of Jupiter. So here are some examples of the lander itself that was built and how we deployed some rovers and we do cooperative robotics between the lander and the multiple rovers. You can see me also in the moon Marcia of Essex with can see. So with this lander, please stay on the slide. So this is this exosolar lander equipped with telescope and synchronicity. And some of this, the rover you can see here was developed by a Japanese group, Akurdi rover, and then they created a company called iSpace that in the meantime, since 2011, grew to have 300 employees and has flown already two lunar lander missions. So next slide can show the exosolar lander that we have described before, virtually on the moon. The next slide shows you how we use also this lander and equipment to test protocol of human lander, rover, and instrument collaboration in space. So the astronaut can go install a new instrument, repair another instrument, put some equipment, inspect the facility. So this is the way also we prepare for this moon village where we have some joint human and robotic activities. So already next slide shows you that in the area of testing technologies and science for the moon and Mars, we started in 2009 a series of field analog campaign where we were in the Utah desert using a Mars habitat of the Mars Desert Station. And there we conducted a series of laboratory and field research in geology, astrobiology, and also in support to some Mars mission, in particular Mars Express, rover mission, exploration rovers, and Mars Science Laboratory, Mars 2020, and ExoMars. And so we conducted some measurements in this landscape, which is very similar to the landscape of Mars. So this habitat is equipped with a laboratory where you can analyze some samples for astrobiology, but also you have living quarter where you can train to be an astronaut and prepare for EVA. So for going to the moon, there are a number of challenges for this moon village, and then here you can click multiple click to see. Please click on the slide. Yeah, you have to get there. Next click, you have to communicate. The next click, you have to operate in extreme environment. Next click, you have to survive for equipment and the astronaut. Next, you have mobility also of astronaut and equipment. Next, you have also to have good partnership between human and robot. You have also the opportunity there next to exploit resources that are present on the surface of the moon, solar power, the soil itself, what it contains in terms of metals, but also the existence of water ice. So what is completely new as a challenge next is that we are going to work on it not only with government, but also with new users, with terrestrial companies, with new space companies. So that's a completely new way of working that is envisaged for this moon village, be it in the frame of the Artemis program or the ILRS, which is the International Symposium session. So after we proposed this concept of moon village some 20 years ago, next slide, we also had quite a significant set of activities with the community when our Director General of ISA really was a strong advocate of moon village. So there were a series of workshops Space Research Center of ISA, but also in many places over the world. Here you can see some top experts in many areas of science, engineering, management, and terrestrial, even some lawyers, some medical staff in the moon village workshop. And next slide shows you that after we have done some of these activities in parallel, we have seen NASA developing a vision for sustainable lunar architecture with the Artemis program, with a set also of modules, different expeditions, including some lunar terrain vehicle, and some the robot, some energy system, and so on. And these are some of the modular elements that we have to prepare, but also we have to test in a kind of coordinated way with the different providers of this different element towards moon base camp and moon village. So now with some collaborators of the laboratory that we have created with the International Exploration Working Group, we have performed some simulation to test some of the activities in this different module. Next slide shows how we test some intravehicular activities. And for this, we have before, not so fast, please. Yeah, we have one before, one slide before. So, I would like to have which is moon base, yes, this one. This is called Young Mars Poland, a program where we train astronaut candidates to live inside the lunar module. And for this, they can spend 1 week or 2 weeks in a place, module, laboratory, without window, completely isolated from the world, and they perform a number of investigations in technology, in science, in biology, in physiology, and you can see some of these astronauts doing some of these experiments. Next slide, called Artemis 3, is a simulation that we have performed. So most of the campaign are with 5 or 6 astronauts, but we also did a campaign with only 2 astronauts on the surface of the moon, like will be the case for the Artemis 3 mission that is planned maybe at 2027. And here we had also the first woman on the moon, Clara, together with an engineer, Matthew, and they spent 1 week in this moon base. They have also to experience a blackout of 3 days, but they survived to live in this condition. Next slide shows you how this Artemis habitat looks like. And so, as you can see, there is a geo laboratory. There is a place for taking the meal of social activities. There is a laboratory. They have also a gym. They have a toilet. And they have a sleeping quarter. So that's an habitat we have in Poland. And if you have some volunteers that want to spend 1 week on the moon, we can bring them to take part in international interdisciplinary group. We have also some grants where we can pay half of the cost of this training. And so I welcome very much some of your young professionals to take part in this and join some international group. They can contact me. Now, it's not always easy to go so far as Poland. So we have also, next slide, developed another project which is called Exospatial Express. That's the next slide. This is a laboratory that can come to your place. So it's a laboratory where you have a laboratory module and then also an inflatable structure that are expanded to a minimum base. So the inside of the module has some science track, some quarter for resting and sleeping, and this has been then built. We have built it and first tested it in Italy, and then we moved it to France for the science festival. We moved it to the Netherlands, and again to Italy, then again to France, and now it's back in the Netherlands. And so this is a nice model. I think maybe you could be interested in your university to do a similar concept of a moon laboratory where you train how to use experiment, but also to train as an astronaut how to live in the moon. Next slide shows you that this is nice to do that close to universities, but also we want to test things like we will be on the moon and Mars. For this, we go to places called Moon-Mars analogs over the world that really look like the landscape of the moon and Mars. We went to the Utah desert in 2009, and then every year we had 2 or 3 crews that were doing there. But we also did a number of campaigns in the Etna volcano, which is very similar to the moon and Mars. We had a few campaigns in the Atacama desert in Chile and Iceland. But but also we have been operating since 2015 moon base on the Mauna Loa volcano in Hawaii. And this I am part of the board, in particular taking care of the research that can be performed there. So next slide shows you how this ISIS International Moon Base looks like from altitude. So it's a solar power, and you can have 6 to 10 astronauts inside. And when they go out, they have a landscape very similar to the Moon and Mars. So next slide shows you, for instance, how the astronaut equipped with the next generation of the suit, they do extravehicular activity, EVA. Here are 2 of my master geology students. They did their work on sampling the surface of the lava flow, but also the inside of some lava tubes. And they analyze the composition, and also even they can some microbial end product of the hydrous alteration. So I did also this simulation. It's a bit exhausting. It's a very physical. So I did it twice, and then after 2 simulations as an astronaut, I played the role of a flight director. Next slide. So we have also on Hawaii a blue planet mission control, where we can monitor the activities of the astronaut, what happened inside and also what happened outside of the base. And this is situated halfway between the summit of the volcano and the beach. So you can then ensure the safety, but also the performance of the instrument, and give them engineering, technical, and also human. So this base is a very nice analog of the Moon and Mars, and we have been operating with many missions since 2015. In 2015, we had mostly very long duration missions, like 6 months or 12 months. But since 2019, we have focused on short duration missions, 1 week or 2 weeks, which are more similar to what you could do on the surface of the Moon. Now, in 2022, we had something catastrophic happening. Next slide. So first, we had to survive the COVID situation, so that limited the number of people that could come to the base from outside the US. But 2022, we had a gigantic eruption in Mauna Loa, and 2 lava flows just came around the base. Luckily, the base is a bit higher in altitude, so it survived. And now it's a great opportunity to study new lunar lava flows, search for lava tubes and so on. And that's what we did. Next slide. In the beginning of 2023, we had a new mission, and the name was Hana Hau. Is in Hawaiian means rebirth. So this was the rebirth of our mission on the space. And you can see me, I was the chief scientist of this mission. The commander of the mission was Hank Rogers. Hank Rogers is really an explorer. He is also the owner of the Tetris game. So he has a bit of money that he invested to build this base. And then he asked me to organize the research that can be conducted from this base. And we have hired personnel for the operation of the base. And we have also some grants for people that use this base for research, technology, and exploration. So that's some of our current program, and we are very interested, actually. We would like to build a similar base in India. One base maybe in proximity of a university, and then after we put it in a remote place that we have to identify. Here is just in short some recollection of things that we have done with India since 2000. I've been more than 10 times in India in various places, and I've always appreciated not only the different places, the very interesting culture, but also the collaboration with Indian scientists, engineers, and collaborators. And we organized a number of conferences in India. I mentioned DYPIU in 2004, where President Kalam came to our talk. We had conference in Mysore, COSPAR. We had conference also more recently in Ahmedabad, and this year we had again. And we are looking forward some also concrete collaboration work we can conduct, not only with ISRO for the space segment, but also with some other universities for research payload development. So my final slide is it, I believe, is a kind of a list of potential collaboration opportunities we could have, and we have already started with some institutes in India, together with our laboratory, LUNEX, that has also a number of nodes in other places of the world. So I mentioned in the US, but also in Europe, also in Asia. So a good opportunities in the field of data analysis of data for the moon and Mars and planets, in particular using new tools of machine learning, development of instruments and robotics, testing them in the lab and in the field, and then developing some small flight instruments for opportunities of mission, which are numerous now from various countries, but also from commercial developers. So organizing together some field validation and science campaign. We also have a specific development where we try to integrate a small multiple instrument in a kind of bench suite package that could fit in a shoebox size package. So we developed some analog habitat, so in Hawaii, in Poland, and now mobile. We think we would like to build a few analog habitat in India. So if you're interested to host one at university, we can help you to duplicate or update what we have done in Europe. There are also some nice prospects of how we can test systems to extract resources in space, manufacture, and also eventually develop some element of future lunar economy. To support that, we also have initiative to educate and train researchers, astronauts, and entrepreneurs. We train them together, and then actually some of them they created the startup, and we have a program to scale up and support on the startup with technical and financial help, networking. Now it's very important to make the whole society public aware of the world in space and how it benefits them. And so we have specific effort on dissemination, outreach, and for this we are also collaborating with members of society at large, from media, from arts, to organize some events where we talk about space. In particular, there is one activity we call Space Renaissance for All, where we organize activity. And there are a number of international events that are like by the IF or by COSPAR, and we are taking part in some of these events together with some expert community, but also we try to bring them the next generation and as well some broader stakeholders. So in short, it's really a pleasure to attend. Some of you are interested in some of this collaborative aspect. Yes, please contact me and we can follow this up. Thank you very much.
Access.
Now, I'm going to explore now. Really.
Thank you.
Very much, and I wish you all the best.
Thank you. Good luck.
Yeah.
Good. ज्वाइन करना चाहता
Somebody wants to join?
इसके नीचे ये लोग सब अलाउ कर देंगे ये और नीचे इनवाइटेड सबको अलाउ कर दो लुट्स है नहीं कुछ
लिस्टेड है उनको भेजा है सर
नहीं वो परमिशन क्यों चाहिए होता है
वो सेटिंग नहीं किया था
वही बराबर एनीवे
Thank you, Professor Fong, for sharing the research and exploration conducted by ESA and ILEWG on Moon and Mars. It was quite enlightening for us to know about the latest research going on this end. It is now my honor to introduce Professor Prabhat Ranjan, a distinguished scientist, innovator, and thought leader whose work sits at the intersection of advanced technology and national development. Professor Ranjan is currently the chairman of Research, Innovation and International Relations of DYPIU Group. He is the founder vice chancellor of DYPIU International University, Pune. He has also formerly served as the executive director of TIFAC, an autonomous body under the Department of Science and Technology, Government of India. At TIFAC, he played a key role in shaping national level technology roadmaps, including those related to space exploration, advanced materials, and robotics. A nuclear fusion scientist by training, Professor Ranjan has worked on cutting-edge areas such as magnetic field diagnostics for future fusion reactors, brain-computer interfaces, and space-based applications. What makes his presence specifically significant today is his passion for translating scientific foresights into actionable missions, an approach that resonates deeply with the goals of in situ planetary explorations. He has been actively involved in envisioning the future of India's role in space science, and in today's talk, he will share his experiences with in situ exploration of Moon, reflecting on both technological challenges and the broader implications of India's planetary ambitions. Please join me in welcoming Professor Ranjan.
स्लो है Sorry, I'm trying to solve a technical problem. So, I'm one of the initiators of this symposium. And the purpose for this was that while India has been working on a space mission for a long time, but actually the moon mission project started Chandrayaan-1. Chandrayaan-1 was not supposed to land on the moon. So it was only to orbit around the moon. And they had dropped one system which did hard landing on the moon, that was to collect data. Chandrayaan-2 was the first mission where landing was planned, soft landing. I got involved sometime in 2007 with Chandrayaan-2 project. The reason I want to tell you this was that even if you're not working in this area, you can still get into the areas. Okay, I was not working in this area. I was from different field, no relationship. I was working, while I'm a nuclear fusion scientist, I was working on wireless sensor network for various purposes, including tracking of wildlife and other things. I'll not go into the history of this, but just to focus on. So I had some discussion with people working in space about can we use wireless sensor network on moon mission. That's how things started. In 2007, there was discussion going on about the planning of Chandrayaan-2, the second mission, where it was going to land on the moon. And actually, first time I have the opportunity to work actually on the surface of the moon. One of the key issue was detecting water on the moon. So, 2007, this discussion was happening about how to detect water on the moon. And they remembered me and they connected to me to see whether we could use wireless sensor network to detect water on the moon. Now, on the moon, there are areas called permanently shadowed regions. These are areas which are completely dark all the time. I'll show you some pictures of that. And then we suggested a proposal. We made a proposal to detect water inside those permanently shadowed regions. We got a funding about 6 million rupees in February 2009. Before that, what had happened, the Chandrayaan-1 had gone successfully and there was some confirmation about water on the moon. I'll not go into this. Let me just show you the picture. So that will be better to explain. So when you look at this picture, there's a crater here. There's a crater here. This crater has a diameter of 19 kilometers and depth of 2 kilometers. It's called Shackleton crater, very wide, 19 kilometer, 2 kilometer depth. Now, these are the South Pole part. Okay. Now, what happens when the sunlight comes in? If you, on the Earth, for example, if you have a well or something like this, even if sun is going at tangent, some of that will get scattered, reflected into the inner part of this. So if you look into deep well, you will see the upper surface is lighted and slowly it gets dark. But on moon, because there is no atmosphere, nothing is there, the light simply passes by. There is no way it can go inside. So inside this permanently shadowed region, it is completely dark all the time. Temperature is like minus 200 degrees centigrade. Okay. Now, why we expect water here? What happens is that on the moon, any asteroids or comets or something which is carrying water, if it strikes on the moon, which keeps happening all the time, it doesn't burn out in the space because it does not have any atmosphere. On the Earth, it will burn out before it lands. But in this case, keeps getting bombarded. That's why you see a lot of craters are there on the moon. If some of them by chance happens to fall into these permanently shadowed regions, they freeze there, minus 200 degrees centigrade. And there is no way they can come out because it's always frozen. So you have a source, so estimated for billions of years that moon has been around, there's a lot of water inside this accumulated. So point was, can we actually detect what is there and see if we can get that water for human habitat and also for other purposes. Okay. So that was the task given. Now, if I have to measure this, one is sensing from remote. Other is that actually, can you go closer and find out what is there? So either you can walk down this as astronaut, very dangerous, temperatures minus 200, or you send a robot. But even robot sending is very difficult because temperatures are minus 200 degrees centigrade, no sunlight and everything. So to manage the robots to go down and actually monitor was difficult. So then we came up with this idea of sending sensors balls. So you have little balls, you throw them inside. When they land inside, they will detect where they have fallen, whether water is there or not there. Okay. But it will not survive for a very long time because temperatures are too low. So it will have few minutes, maybe 10 minutes, 15 minutes time before it will die, electronics will die. Before that, it has to communicate to something outside where they have found water or not found water. So that was the concept we put forward, for which we were given the project. This now what we had to do was, these red balls are the ones which have short lifetime. Short lifetime means they do not have enough power to keep it warm for any time. So they will die quickly. And there are these blue ones which have little more mass. So they have little battery or some heating mechanism to keep it surviving for a long time before it communicates. Idea was to throw these balls. Wherever they fall, they detect water, it is yes or no. And they have to communicate to these three, any one of these three. These three are connected together through wireless communication. Why we have chosen three? Because of redundancy. So now what happens is that these red ones, they detect water, yes or no, and send the communication to wherever they can connect to any of these. And then these three actually replicate the data among each other. So same copy of data is available to each one of them. Then any one of them establishes connection either with a rover or directly with the orbiter. All the data will be transferred. Okay. This concept actually had picked up from a project I was doing to monitor animals, wildlife. There we had exactly applied the same concept. We copied the same concept where these animals move around in the forest and there's no way to communicate. So they used to communicate with each other through something on their neck, and the copy will be communicated, and then any of the animals comes closing to a receiving tower, the data of all the animals will be transferred. So this was the idea that we had put forward. Now what I'm going to very quickly talk about is sensing mechanism. So how do you sense whether water is there or not? That's important. What is the kind of electronics, what are the communication software to be done? How do you deploy these systems and package it? So to detect water, we use a tuned diode laser-based systems. This was used on a Mars mission of NASA in 1999. And they used 1371 nanometer infrared tuned diode laser source. I will show you the picture of this. So basically what happens is that you have a source of laser, it reflects with a mirror, and there's a sensor here, and there's a place where whatever sample you want to put in is put in. So if ice is there, there's a little heating mechanism. Whatever is coming out is actually gets in the path of the laser, and it changes the thing. So laser is coming like this, getting reflected back, and there's a vapor or something like that here, and this laser characteristic gets changed depending on what is there. So this was a thing that used for Mars mission. That mission had failed actually, but the sensor was developed. It had costed a lot of millions of dollars actually at that time when it was developed by NASA. But then due to new technology coming in, the cost has come down. So we had a tie-up. So in fact, you can see this is the one that was landed on the Mars. And these systems are inside. I'll not go into those details. So we picked up this concept. You can see the size of this. And we actually use this with another institution called Samir, which actually is in IIT Bombay campus. We tied up with them to develop this part of the work. Okay. Now, how do I deploy this? Okay. So there are two ways to do it. There are two companies which have worked on this. I'll just show you quick examples of these. One is this was tested on August 2005, where you have a launching system just like cannons or missiles, which actually throws this, moves around and throws these sensor balls into the crater. Then how does it, you'll see another thing, how does it stand up and communicate? So this was another mechanism developed, so when the nodes fall, they will actually stand up and connect to the thing by proper arrangements for communication. And there was another one which was sensor bus deployment. So all these things were done so that when it lands, things will happen by automatically, there's nobody to help it out. Now, this project, we got funding, but within 3 months, we found that mission plan had changed. And while we had the fund, the mission cannot go. So I have to change. I mean, if I want to send something, I have to change to another project. So that time, we thought of lunar seismic sensor node. And there was certain reason, I'm not going to those details. So we submitted a new proposal right after that. Now, seismic activity monitoring on moon is very, very important. It has implications for the formation, evolution, and current state of the solar system. In fact, this was a suggestion given by one of the physical research laboratory scientists to me. He said that water is important, but this is even more important. So what was done in earlier Apollo missions, that every time it was landing at some place, they will deploy a seismic station there. And the next landing, it will deploy, say, 20 kilometers away or 30 kilometers away. So they had a network of seismic stations across. Astronauts used to go there, set it up things. Used to cost like something like, I don't remember exactly, maybe 20, 25 kgs. Okay? And then the data would be collected. Now, when we started to develop this, let me skip this part. Okay. Now, one deployment possibility by astronauts, which India was not sending, so not possible. Other is something called penetrator. That means from orbiter it is dropped and it penetrates into the ground. And third was that something that is carried by a lander and deployed by a rover. So we had opted for this one. Now, in the Apollo, the seismometers are set, in fact, not 20, it's 1100 kilometers on a side. So it was a very long distance, depending on where it was landing. The observation continued to 1970. So these are the only source of in situ data for seismic activity on the moon. And there's a lot of gap that exists in our knowledge of interior. The lunar waveform, seismic waveform, is very different from Earth. Okay. One is the rise time to peak is very large, then oscillation continues for hours. On Earth, it lasts for a minute, few seconds, or maximum 1.5 minutes or 2 minutes, not more than that. If it lasts more than that, we'll all be very disturbed. So, through Apollo mission, a lot of events were captured. However, 60% data was not of good quality, so it could not be analyzed. Now, on the moon, the seismic activity is very, very, seismic floor, I would say, seismic activity floor is very low. That means the noise level is very, very low compared to Earth. On Earth, you have a lot of disturbances, but on moon, there is very little disturbance. So seismic noise floor is very, very low. At the same time, the intensity is not very high. Like on Earth, you can go to 7, 8, 9 Richter scale. Moon, it is maximum like 5 or something. But because 1 order of magnitude lower noise, so the dynamic range is quite high. So detecting of the small events is very, very crucial. There are different ways. One way is that you actually hammer some place and you have an array of sensors, detect these, then you move the hammering mechanism and detect this. That's one. That is called refraction seismology. So what we had planned was to have 4 nodes. Now, important thing here was that we were told that it is a single mission and I have to place 4 nodes at different locations. I cannot go very far off because the rover cannot travel long distance. In 24 hours, I was told it can only travel 10 meters. That means half of this room. So first I thought whether it is of any use or not. I had visited Jet Propulsion Lab in NASA in 2009. I had discussed with them, and this is very, very useful. It will give us data not for depth of the moon, but subsurface structure, 8, 10 meters down. Things very important for structures to be built there. So then we worked on this. So we decided to have sensor networks and then nodes. And then one of them will also have capability to pour in an electric and thermal probe inside the regolith. So we had 2 possibilities. One was you have these connections and there was a gateway. This was related to communication. So these nodes are there and they are communicating to rover, or there's a gateway which is connecting to orbiter. These are 2 options. We actually opted for this option. So this was, for example, a design where you have, this is on the rover, which is collecting data from all the nodes. This was one of the specific nodes. I'll not go into details of these. But there was a geophone kind of thing inside and the other sensors, along with solar film to capture energy. And there's another one which had all that, and there was a probe that could be inserted into the regolith. It can be pushed into that. So this was a special. Out of 4, all were similar, except this one, which had this possibility. So it can go inside. So for example, it is inserted inside, it will collect data from there. Now, I'll not go into details of these, but basically what you do is that you cannot keep on running seismic monitoring all the time. So you have to conserve energy. So what you do is that you periodically wake up, see if there is any activity, if not, sleep. If there is activity, continue recording for a long time. So this is all to save the energy. It's a very, very important part. Let me leave out this part. Now, how do I get the seismic activity monitor? So there are various possibilities were there. We opted for something like this. We purchased actually. And then there was activity going on in Jet Propulsion Lab. Tom Pike was one of our collaborators. He had developed something, had moved to Imperial College London. But that was an analog system which would give very high dynamic range. But we wanted to go to digital system actually. So we're discussing with them to actually convert this into digital system. In parallel, in 2009, I had visited HP lab in Palo Alto because the award we had won. And there we found somebody working on printers had developed a sensor which was very useful for this purpose. We saw the demo also. So I will not go into details of these. Then we made a prototype electronics system which had, this is the seismic activity monitoring. There was DC to DC converter, gets multiple voltage levels and so on. All of this we had done in 2009, around 9-10. Now, how do you couple the seismic sensors to the ground? It's a very important part. On the Mars, one of the NASA mission, first one, they had put seismic sensor on the lander. And they got a lot of data, but later on they found that it was not seismic activity, it was the wind moving around which was vibrating the lander and giving wrong information. Then they did a lot of experiments and they found that if you hammer the thing into the ground, then it gives more. So in Jet Propulsion Lab, they were doing a lot of experiments. I had insider view to this because one of my friends was there. Not only friend, he was my apartment mate in US. And then he told us that how they had done this testing and they found that about 30 centimeters inside the lunar regolith, if the seismic thing is coupled, it will get the real information. So you have to have spike. And then we did software, other things. I'll not go into that part. Time synchronization is very important for this. I'll skip this part. Now, when you get this data, it's important to do the modeling part. We didn't have expertise. So we connected to various people at different places. And we connected to a person in US. He said that I'm not doing any more work. His PhD is over. Then I tried to connect to Japan people. There's very little work being done at that time. So we had to, after lab tests, we had to carry out various testings and verification. I'll not go into this detail. This project did not get funding. But what happened, which I'm going to talk about later part in the day, in 2010, there was a mission change again. Then I was requested by ISRO to actually plan out a system which is going to do a number of experiments. The details I'll share later. That's where we connected TC and Sean Whitehead in 2010. Okay. The reason was that initially the Chandrayaan-2 was an Indo-Russian collaboration. And then Russian rover plan dropped out completely. So we got more payload and eventually a Russian lander also went out of system. And finally Chandrayaan-2 went in 2019. So then I was asked to develop a system which would do surface and subsurface exploration of the moon. And that's where we named this project LUSEX, Lunar Surface and Subsurface Explorer. It was to explore geophysical property, geochemical properties of the lunar surface. And Sean Whitehead and his friend and TCNG, both of them as a team, we connected at that time. And they were recommended to us by ISRO only. All the communication they had was sent to me. That's how TC connected and since been 15 years, sorry. And he's traveled to India at least 5-6 times for this purpose. He had gone to my earlier university as well. And Dr. Tom Pike was in Jet Propulsion Lab and he had worked on seismic activity for Moon and Mars. And Dr. Tom George was my friend. He's from India only. He was head of MEMS group in Jet Propulsion Lab. Now he's come out, not only now, maybe long back also he came out. So we actually planned this system, which I'm going to give more details later on. Some of these systems had been developed earlier by TC and Sean Whitehead, which had gone to Mars mission in Beagle 2, which actually crashed. So I'll talk about this in later part of my thing. So I will stop at this point. Thank you very much.
For talking to us about the possibilities of engineering solutions. Our next speaker brings a truly unique and interdisciplinary perspective to the world of planetary explorations. Dr. T.C. Ng, sorry, I'm finding it difficult to pronounce your name, so I'll stick to TC if that is okay. Yes, okay. So he's a practicing dentist and researcher from Hong Kong, whose work spans beyond clinical practice into the development of precision instruments and microsampling tools, expertise that has remarkable relevance for planetary science. At first glance, dentistry and space exploration may seem worlds apart, but as we delve deeper, the parallels are striking. Both fields demand high precision tools, the ability to operate effectively in constrained environments, and a mastery of biomaterials and surface interaction, all of which are crucial for designing instruments for in situ sampling on other planets. TC has been a part of collaborative efforts to apply micro-instrumentation concepts to planetary explorations, helping ensure future missions can collect meaningful data from diverse and challenging surfaces, be it lunar regolith or Martian dust. Today, he will speak on planetary sampling tools that should cover all sampling concepts for different applications, offering us a rare cross-disciplinary insight into tool design and functionality. Please join me in welcoming Dr. TC to the stage.
I gave you this one, but I don't know computer. You can help me to press it. I'm TC, you know, I'm very old. I'm 70 something. But I don't know computer really. All my concept in drawings, hand drawings. I got about 12,000 drawings, you know. But my interest not in planetary exobiology and also in cancer, in dentistry, in Egyptology, all have quite a big full result. I will tell you, you know. Sometimes when I talk about planetary science, you know, it will be very boring. I'll tell you something about Egypt and so on, you know, yeah. But I give you a very brief idea, you know, yeah, what's it all about, you know. First slide, this is... actually, Professor Ranjan wanted me to design a tool for your Chandrayaan rover. I finished it already. It's called a cheese knife. It's only 1.5 pounds. 1.5 pounds, maybe 2 pounds. It will be equal to Beagle 2 40 pounds of instrument, you know, yeah. I worked with, in the late 80s, you know, I started with a pair of forceps, a dental forceps. It got all the secrets of planetary exploration, really. And it was made in the most German company, Escalab, you know. And after that, I spent a few decades in planetary, planetary tools, you know. I was selected by a UK team, a Beagle 2 team, for doing rock coring. Actually, it's a biggest joke in the world. It's a really biggest joke in the world to select a dentist to do do the job, the most difficult job actually. And there are three kind of profession is suitable for this actually: microsurgery surgeon, clockwork repair, and dentist. But dentist too is the right size, exact the right size to grip rock powder, you know. I'll tell you one thing, you know, when you do, all the secret of Mars is inside the rock, actually, not the soil. Carbon-13, carbon-14 isotope, you know. But how do you drill it and pick it up by one instrument? You need a special kind of drill, you know, yeah, that's it. And I have started from early 90s. I was working with ESTEC, ESA. I started the micro N effectors, the micro N effector for do exobiology, and I can tell you all the secrets, you know, of and I introduce a cheese knife to you, but it might be a biggest joke in the world, in a cheese knife, you know. Yeah. No, I gave it to Dinesh, you know, already. I give it to you already. No, I'll tell you other projects I'm working, you know, in if you have heard about the Great Pyramid in Egypt, you know, they have been solving the problem of air shaft of the Great Pyramid for 4,600 years. MIT got it wrong, German got it wrong, and British got it wrong. I belong to the British team. And one day when I was swimming, you know, someone banged my head. And I figured out how the whole idea, how the Pharaoh Khufu, and you know, there is got a magician called Jedi, and an architect called Hemorrhoid. I know what they're doing. And I tell you, but don't show the slide to others. National Geographic not informed yet. You know, there's a guy called Professor Sayer Haras, the most big temper Egyptologist, you know. He agreed. He said yes. That is this is called HVT theory. HVT theory. I'll tell you about cancer also. It took me 10 years to persuade Israel Institute of Technology to listen to me. 10 years, every day. Come on, listen to me. Finally, they listen to me. And we're working with a Nobel Prize winner and a Harvard oncologist. I think everyone got it wrong. The cancer, if you were treating cancer like this, you know, you will all die. I tell you a little bit of it. He accepted two of my concepts. The last one, I found it out just only a few days ago. He said that yes, yeah, that is very close, very close. Yeah. The cheese knife concept for the Chandrayaan is only one maximum motor. And the cheese knife is actually a cheese knife. And you got a sampling circle in it, you know. And I tell you, if you want to replace the cheese knife concept, you need a Russian mold. Russian mold is about 2,000 grams already. And you need a sample fattening device. And you need a robotic arm of all the N effectors. That will about 20 pounds or 30 pounds. But we'll go down to 1.5 pounds. There's a German working with me who say, no, 2 pounds. I said, no, 1.5 pounds. Now, can I introduce a tool to you? You know, NASA is working on RAT. RAT is a rind grinding surface tool. This by Honeybee Robotics is 6 pounds. And the rock coring, NASA using 100 pounds. That means 106 pounds. And we have designed a tool called GCC that is 1.3 pounds, equal to 106. Obviously, the NASA one is much better, but actually, now Emirates, Turkish, everyone are talking about rock coring device, GCC. I think India one day will use it because of the low payload. Because if you talk about 40, 20 kilo rover, you can't bring a lot, you know, yeah. This is the last slide. The first slide. There's the last one. I added this morning, that's all. This is all the last slide. The first slide is not this one. First, I gave it to Dinesh already. No, this is the same. But the first slide, Dinesh, I forgot it. I gave you. No, this is the last one. Maybe I talk. This is a Russian mode. Russian mode is about 3 or 4 pounds to something on the bottom or whatever there under Mars, you know, except sample. And then you have to distribute the sample and fatten in the sample. And the lower, can you, I don't know how, yeah. And this is the red one is a cheese like. This is the N factor. So then how many N factor put on? The robotic armor, how many N factor on the vehicle tools? This is maybe about the altogether 40 pounds, 50 pounds. We have to go it down to 1.5 pounds. Everything included, you know. But now I don't know computer. Yeah.
It's working. Yeah, you come this.
Yeah. Oh, my voice is very loud.
Yeah. No, but the microphone doesn't pick up the people who
Oh,
are
okay.
on the distance.
Is it? Can you hear me?
Yeah. There are many versions.
This is the last slide. The whole slide is in the. Yeah. Somebody attends. selected by UK, to the rock quarry in 2003. But we won actually #1 in the European Space Agency for agriculture with micro-energy factors. We won everything, and they choose us. And they say that, Professor Richter, the vehicle is really, if you can do vehicle, you can do anything with it. The payload is only about 140 pounds, including everything. The instrument payload is the highest in the world at about 24 pounds. Now, the trees are there. Can you go back down, coming? Oh, coming up. Yeah. Now, can you see the trees? They got all the secrets of planetary satellite. And our approach, UK Space Agency. You have to work really hard every day and night, I want everything, all the testing and so on, before you be selected next phase. Now, there micro-sampling. Actually, micro-sampling, there's only one team in the world working on this. And we produce this is from ELCOM. And further forwards, we are all working together. Now, this is the rock core. The rock core is only about 4 literature. If you want to read ourselves, you have to do the rock core one part. One part is 450 grams. That is one model of Coca-Cola. It is actually it's a biggest jewel in the world. Because the last one, the jewel is 100. Of course, you can do deeper, but as long as you get the raw powder sample and going to GCNS, actually, knowledge input will be maybe really the same, maybe 50% less or something like that. And this is a rock core here. And here, this was 2 decades ago, 3 decades ago. And next is rock coring. Now, rock coring, I've given you your team the GCC already. GCC is brine grinder. Now, when you do sampling on the rock, okay, you have to remove the brine surface. In 1999, I said the part 5 forgot to bring the brine. Then in the 88 hours X-ray will be doing the force reading. You have to do brine grinding and then brine cleaning before you do brine coring. Now, we're doing everything in 1.4 pounds. E-resistant. Really resistant. If you have a rope for only 20 pounds, you can't bring anything. You bring just 1 tool, and the whole world is watching this tool now. I tell you, in India, eventually you go to Mars. But your rope maybe 40 kilos. Your robotic arm. APX, Cycles, this is the brush, this is a coring, and I gave you all the dimensions. You use it maybe 10 years time in the past. So we decided this place. You can have a better design than this kind of 1.4 pounds of B functions. Next bit. Now this is the corner, okay, and the twisting 30-degree. Next bit. This is the one point. This is a tungsten carbide. You will use it one day, for one month. Next bit. The surface pebbles and the soil actually I designed quite a long time ago already, but I say, I don't think anyone will use it. But you know, when my German partner, who's Richter, I've seen it, they say, yes. There's nothing in this world picking up pebbles. I think it's surprised, you know. But nothing yet on moon surface you can pick up pebbles. And which pebbles is good or not, soil, nothing like this. I given all this to you also, you know. This drill, you know, how to release soil from the threading is by a vibration. And then the soil going down. And then the secret chamber. This secret chamber is also used by NASA, you know, for honeybee robotics. Secret chamber, top right, reverse, top right, people get it done. But it's not necessary. We have a camera here, a brush here. I gave you all the drawings we have been already next. Now, this, all this, you know, we will use it, but I don't know why they haven't thought of it. No, you know, next, next, we'll go to another topic. Now, this is subsoil voltaic gas. This is for the South Korean. South Korean team is very demanding. They want gas, helium gas. The only way, but I don't know computer. I just enjoy every day. It's just a mental disease. But if I don't enjoy how to store the gas, and another secret is, you know, when you go to GCMS, the outlet has to be the same as the outlet of soil sample. Otherwise, there's a lot of problem. That means that the soil sampling, this exactly the same as the Russian war. It's no big deal actually. And the gas is going through here, and how to get the gas and soil within one entry of the system is very difficult. It's very, I will tell you in a minute. Next. Now, subsoil and sensing. We're talking about the Indian team now. Next, can they go down? Now, this is I give it to the because this is I'm having him on actually. You put all the sensor inside, and then there's a mirror, there's a window here. That's it too much for it. You know, how can you have a Geiger counter, what a helium and so on sensor, and the handling there, and the signal will go to the rover. Then one day, I thought, okay, he's not going to win, you know. Then we come to the cheese knife. Next, this is a cheese knife. I try to cover it up because we call it the moonlight step. No one is very happy with it. Now, this is one motor. The green part is a motor. You can have how many sensors as possible. This is the red. You will go up and down, and this is the line. This is a circle. This is a sampling chart. Simple. You know, the soil of all this negative charge, the 700 volts, and we need a metal positive charge. There, you know, the retention of the sample. There's so many forces. You can have undercut force, electrostatic force, and because in between the cohesive force. But Professor Ranjan told me, how can you clean it? Affordably, to clean it, we add a brush. When you go up, we replace the upper part. If you use a handling unit, it's too heavy. We use solenoid. You know, where's the helium? The helium is only 10 cm under the wood soil. It's very easy to get inside. Why you use a drill? It's too much energy. You use a cheese knife blade. The light A will be about 1 mm to 2.75 mm high extent high stream. Neckline or stainless steel, whatever. But this part is very different. Cohesive force, retention force, electrostatic force, but feeling part is very. I put it in a brush here and an upper brush here, and you have ultra solenoid vibration. And the brush will remove the particle from inside. When you go into the soil, you automatically reveal the old sample by new sample. But well, how can you get to 10 cm with new soil? Then you go down vibration, and you go down to a certain depth. The vibration longer, much longer, maybe a few minutes, and there will be exchange of soil particle of the new one by old, or old one by new. It's not perfect. But I tell you, you can do a sleeve inside over and there will be a lot of jamming. Do it simple. The simple thing is you just have some soil here. The soil, this circle is exactly the dimension of the sensor. Now, how can, when you go up here, the soil, the end effect immediately coming to contact 90 degrees. We need the sensor to be exactly such coincide with the circle. That is trick. But I add a few more this morning. Yeah. When you have a lot of sticky soil, you know the soil of all is very sluggish, very sticky. We have a flattener here. A flattener here, then you can make a linear sample. And maybe you need a two end here with a mini stopper. That means the two sensors will just a little bit apart. Now, but this is a lot of research here, a lot of research. This one motor, a solenoid vibration, no handling, too much pain already. This why it called one night stand. Research. And then 多点的录音看到，auto cleaning, auto sensing, auto sensing. I don't think you can do more simple than this. Yeah, don't make it complicated. At first, how to clean it. When I work with village, the end effect, do we have to choose a new one? It's true. We can hammer it. And then, on the last surface, it's so dry, all the particles will come up. But one thing is, I'm not a scientist. If you can, this brain is possible. If you can have some method to make it negative for release the soil, that will be perfect. But I don't think so. I went to the internet, then you use a brush. Ultrasonic vibration. When you go inside the moon soil again, the old soil will be replaced. And the auto vibration will release the old soil back with a new soil. Okay. When you go down, you do vibration more and more duration. The exchange of soil will give you maybe 80% of new soil. What's so big deal? As long as you got results, what's so big deal? The 20%. They're all the same. We need the same actually. Next minute. But plume sampling, we are working with Bernard Forens in Harvard University in astrobiology. Now, I tell you, my whole aim is to the first one to unlock the astrobiology. Virtually, I look at concept conceived. I give them about 30 or 40 concepts. But at first, the latest nets. Actually, the final result of yesterday is actually you can no fundamental, no energy. The energy will be stored when it's landing in energy. may be a heating sublimation energy, and such that the plumes will push up the bottom of the net. But this is just starting, that's the problem. But this is how the lander base, how do you remove the lander base, how it is all outdated already. But next is, we have a laser triangle coming out. The laser triangle is moving all the time to form a inverted cone sublimation, cones sublimation. And you know, the only thing you can find life is science. And because, you know, have you heard of encyclopedia? Encyclopedia is the wood of Saturn, with 4 tigers at the bottom of the planet, with all the plumes coming out. And they find carbon already. And people are not going to Europe anymore. It's science. And because the land will be exactly the people. It's open, and the base of the land, the bottom has to be detached. You form a funnel, and you top, sit on the top. The total may be about 4 feet, but you landing up a 1 feet left. Some of them will push up. They are working on the lasers inverted triangle for being ready in 1000. This all the problems project. And this is a laser fission laser fission laser. I think it's too difficult, too complicated. Next. Now, the universal sampling, you know, next, they work with Prabhat. You know, the Japanese have a very nice book presentation. They got a robotic arm, you know. But if you have all the mission, all the concept put together, rock core, all the time get sampling, laser supplantation, okay? And the difficult part is engines. How do you go to T7? You deflect coming up and under one entrance, okay? And all the sample will go into one entrance as well. That is the most difficult. You know, you can't have 2 engines in the T7. Next question. Now, this is a reflection of the probe going back to one entrance. Yeah, this is in the future. I tell you, all the tunneling tools are enough for your mission. I can figure another 50 concepts, okay, but not necessarily. Subsoil, modified gas, Korea is quite complicated. The G-slide is, I think it's good enough. It's achieved everything of a people, actually. Now, I'll tell you, tell you a little bit more about planetary science. I give you something really exciting, but don't repeat it. Don't repeat it. Next. Now, this is the magic of the whole. You know, they have been talking about the air shaft of the Great Pyramid for the last 40 years. A robot going out and find you know, from the pre-chamber, we send the robot there, and you stop. Suddenly stop. Why? And then upper, they go up to the top. But lower, they stop here. Lower, they stop here. Upper, go up to the surface of it. You know why? No one, everyone said, here, something behind. No one is put, you know, this about 45 feet in front of the surface of it. No one is going to put your money in here. The truth is in here. And one day I was swimming and you bang my head. This is the whole architect construction of the field. Without the HVD field, they can't build this. This is the star. This is the star, the Orion star. Orion star is 44 degrees, 4,600 years ago. You only see it once per day, wonderful day. And the angle is exactly in the pyramid. And the polar star, you can see it all the time. And this is a square. The whole thing is how to, this vertical plane and another vertical plane is going to meet together to build a two vertical. This has not been exposed in the history of God. We will be exposed, and the critics say, yes, I agree. This is the magic. 4,600 years ago, I'm so sure that one night they had a party. About 3 nights ago, we were king, Pharaoh talk with a magician. The magician had Chuen. This was about Chuen. If you want eternal life, your spirit has to go to the star. The star, Orion, the 3 stars. The 3 star replication of the 3 star except the pyramid replication. How do you go to the star is from here. The kingship, there's a coffin here. There's no coffin here. That means it's coming. This is the plan how to build this. This is why when the 2 or 3 there's a live broadcast and they find there's the door. Then another door. This is 8 times X times 8 inches. Why this social 8 times 8 is the bottom of the lift. And one day I was swimming. That's it. And everything comes like. But I'll tell you another thing is boring. Come in. But I'll tell you about cancer. Next. Cancer. It took me 10 years looking at the goal. You know, there's a very famous scientist called Professor Shyama. Jewish is very clever. Very clever. I said, yeah, you're doing wrong. Now, I tell you, if you carry on treating cancer like this, everyone will come. You know why? Because my knowledge is totally really, but all the concept I did in secondary school, but it works. I'll tell you one excuse is cycle. You know, because the is quite boring. I tell you, if you cancer, there are 3 mistakes you made. But metabolism is random. From primary to secondary growth, 1 year, nothing comes on. 1 second, 10 minutes. Then you got only 4 minutes to stop there. So cancer. Only 4 minutes, 4 circulations. And you go to secondary. And now we are putting a wire in the inferior reticulum all the time to attract the secrets. No chemotherapy. Another thing is if you have cancer, don't you ask surgeon for it. You will never go. Because no one knows the safety margin that happens. We are now doing any factor. It's automated. Third, I advise him to do it is in fact. In fact, it's easy. You have a biomarker touching the cancer cell. And they say that we use radio frequency. Radio frequency heat the iron, but heat the iron, heat dissipation. Not enough temperature. Dance with the iron. When you dance with the iron, we use an iron that is sharp on, you burst the cell. That's it. That's it. That's but this is the worst thing in dentistry. Dentistry, total failure. Really total. The worst thing in dental is done. No one can end the for mankind. The Colgate is taking 44 billion US. Big money can end it. There's a very easy way of doing it. Now I'm number one part. We are sustainable. Because there won't be able to pay. There won't be too much. It's just it works. I hope you enjoy it, But think about the cheese knife, Don't make it so complicated, Come and go down, get the soil from one gram of soil. Well, when you put the soil up, you have to spread it out anyway, evenly. Now you get it on the side of both sides of the cheese line, and the sensor going close together, and just so perfect data. The most difficult part is how to put the sensor just perfect data, touching the surface. How to clean it. Sensing, auto sensing, auto cleaning, not auto sensing. One motor, 1.5 max. Thank you for listening. Any questions?
इनके बारे में पता है
It's very easy. One more and one around 5 pages, 8 pages. No. Pages equal to 8 pages. They are very worried. You won't have it. But the point is, if when you go to the moon, I think the helium is what we are talking about. Helium is here. Anyway. Yeah. And when you keep it down, you don't see the sun on the then the twins is the any factor, the gravity of the medical by entry, and the surface is both sides. You can have 4 anyfact, 6 anyfact, because of the But then after examination, the professor asked me how to clean. The cleaning is about above and below the sensor. And also solid soil. And also when you keep it back up, the whole soil will come out. And then you go back a little bit, you switch on the solid. Okay? You will come out in place by yourself until you go to the depth. And you turn it on, and the exchange of the circle sample on yourself by the angles. And then you go to another side. But the wood is very dry. So it's not very. You can't also solid filling water, not necessary. And always the almost itself. So this morning I read a fact that the human cell may have all things. Remember, the blue story is the negative chart will stay. And you have a positive chart there. What was use 10 and then I need that to be. Now we have over I play the list of entries so that before the family that will be underwent just something that I did, and then I woke up to be enough. But this is the best I can. But I can, you can, I can do whatever you like. But not five hours. It's not perfectly you can. At first they said, Astronomy has no security. At first they want a wrong form. Of course, it's a actually, so many things. What I think, she's like, is so attractive. I think on the moon, you're not doing science, you're doing performance. That some instrument can't, simple and be something. If you want to be painted, she's like, you have to use a whole button. Get the thumb out and take it out and stretch it out and cut it and done it one. And move one arm, then for the arm. 1.5 seconds. Then it 2 pounds. If you talk about it, this is the best. What do you think? So maybe you don't be banana in the face. It's so easy. When you look at the drill, again, life is a negative charge with a fixed positive charge. It's more everything in soil. What do you think? Any question?
Think of a cheese knife. Thank you, Dr. TC, for reminding us to think of simple design solutions for planet exploration. We will take a break for lunch now. Lunch will be served in room number 551 for all those who have registered this morning, and will reconvene at 2 p.m. People who are online, I'll just check.
We'll be at 2 o'clock after 1 hour after lunch.
Welcome back, everyone. Now let's welcome Mr. Dinesh Kumar. Morning. Welcome back, everyone. Now let's welcome Mr. Dinesh Kumar, who works as an assistant professor in the School of Engineering at Patil International University. Professionally, a mechanical design engineer with 28 design patents and 9 utility patents, he is currently working on the Moon Mission project at DYPIU. Let's welcome Mr. Dinesh Kumar.
Yes, sir. Just share. Yes, sir. I think it's working. It's not working. Hello. It's not. Hello. Yes. Good afternoon, everyone. So my topic is actually I am working here as an assistant professor. So from past 6-7 months, I'm working on design of in situ exploration of moon regolith. So actually, while designing a component, it takes lots of time and process and expertise. So designing on a particular paper and then designing into a particular prototype, it is a long process. So actually, now I'm going to explore that particular, what we have did in this particular project. So in situ exploration is actually when we are going on the moon and we are going to get some samples and test it over there. So there are lots of various methods we are going to use, like robots, drill analysis, and other components which we use. And these are actually the challenges which we are facing. First of all, lunar regolith, actually it is not a homogeneous mixture. It will be a combination of, there must be some glass transition due to meteoroids. The particulate size, it is going to vary between 40 to 800 micrometer, and it is going to vary. And at the end, there is a lots of that cohesive forces which are going to affect the that charge onto the component. There is no space, so it is going to stick onto the component, and it is going to make that things harder to get a sample onto the component. So these are some of the pictures I have taken it from that source Science Direct paper, and this is actually sourced from NASA Science. So these are actually the moon size. So you can look at over here. There is some that regolith component, soil, and there are some pebbles and cobbles which we are onto the component. And this is actually taken from NASA. This is actually the brown soil on over there. So our main purpose is actually do some exploration onto the soil. And we have designed 2 components. One is MSD, moon sensing drill, and second one is SPS1, which is called as soil pebble sample collector. So in this one, these are actually the scientific challenges we are going to have. And these are actually significant what we are going to take. First of all, geological and geochemical about the moon's history. Second one is actually analysis of different layer, and it is going to give us the lunar environment, and at the end which we are focusing on. This is the in situ resources such as oxygen. From oxides, water, we are focusing on water ice, as we already said that we are focusing on ice. Helium-3, which is actually due to solar wind, and at the end we are looking for that materials and construction material for the construction onto the moon if we are going to happen. So these are actually the planetary space sampling which we have done. It is actually key goal exploration, fine grained soil which we have already discussed. Then we are going to have pebbles and cobbles onto the surface. These provides us actually geological and chemical clues, so which we are looking for. So these are the project which is already happened. Various tools has been already used like scoops, then projectile based samplers. And in the past mission, there are some limitations. Like if we are going to drill, what will be the drill? There must be some temperature variation, as we have already looked at the Chandrayaan-3 data, which I have already added. There is a huge temperature variation from the surface to that the depth which we are looking for. Then these are the some outdated projects. Chang'e 15-2020, it used 1.7 kg of lunar surface by using a scoop and 2 mm drill, 2 meter drill. Hayabusa 2019 used a 5G tantalum material, and this is actually RSS NASA used for this one. And there are some challenges and limitations which already done. Drill was observed at the regolith particle during core sampling. That what are the actual limitations, active measurable vibration or internal, which TC has already discussed about the vibration, how we are going to use vibration to get the sample out from the surface of the drill. Next is containment to preserve sample integrity, which we have already discussed. So these are some of the parameters we need to discuss. Actually, these are going to affect the sample as well as while we are drilling. There are some major like drilling and excavation, how it is going to work. Thermal environment, as we see, sir, have already discussed that it is going to be a huge temperature variation in that craters. Then there is a vacuum condition, dust hazards, and regolith related sources. So these are already listed over here in this PPT, what we have done. Then drill clogging is one of the major issue. So this is actually team which we have worked over here in DYPIU. So first one is SPSS. So soil pebbles sample collector was the first project we were looking at. So it is actually having 3 modes. First one is stowing mode, drilling mode, and vibrating mode. So while carrying that drill mode onto the moon surface, first of all drill mode. So while drilling, just look at this animation which we have prepared. So this is the drilling mode. At the time of drilling mode, the arm is going to be lift up so that we will have space to dig it down to the moon surface. Then it is going to move downward with a rotational, which we can control. So there must be some sort of power consumption and that RPM and torque onto the surface. And these helical that threads onto the drill is also going to affect the power consumption. If we are going to decrease, it will limit down the rotational speed and depth of that cut. If we are going to increase, it will have a huge cut and it is going to have more power consumption at that time. Second one is vibrating mode. In the vibrating mode, it is going to vibrate. It will hit continuously onto the drill. And due to that micro vibrations, it is going to remove the particles from the surface and it will be collected in that secret chamber over here. And next one, the secret chamber at the end is going to be open and closed at the time of that sample collection. So this was the concept we are working on over here. So major parameters are the thermal consideration, stress consideration, and environmental consideration. So whenever we are going to have the variation of the temperature, there is expansion and contraction of the material by which there is internal stress generation onto the materials. This is the major focus. And these are actually the benefits and advantages of these we can implement on Moon, Mars, asteroid, soil collection, and targeted rock. The second one actually was the moon sensing drill, MSD. So it had 3 sensors over here, water collector, then it is going to be helium-3 sensor and in the environment humidity. So there is a drill bit, gear rotational. If we are require the huge torque, we can convert it into by using that gear dimensions. So this is the Chandrayaan data, Chandrayaan-3 data, which we have collected. So at 0 degrees Celsius, it is going to be approx 48 degree at the surface. When we are going to below that surface, it will going to decrease and it will be approx -10, and if we go longer, it will always decrease. So due to that temperature variation, the lower portion is going to be at low temperature as compared to the upper one. So due to temperature variation, expansion and contraction, it is going to have stress generation inside the material, as there is no space between that component to move. And this was actually the MSD component. First one is hammering unit, electronic unit, drilling unit, and the sensing unit. So this is actually, we have designed it in DYPIU. These are internal components. This is the motor, which is connected with gears, and it can increase or decrease the RPM. This is the hammering unit, which is going to be connected via cam. So when there is a high peak, it is going to be onto the up and it will vibrate continuously, which is going to apply some forces onto the drill, which will help us to drill onto the moon surface. And this is actually the animation, how it is going to work. So there is a drill, gear rotation speed, and this is the casing which is going to protect the components. And this is the cross-sectional view where we can see all the components. This is the spring to absorb energy during the lift, and it is going to release at the bottom. Then second one is the MF cam we have used, gear unit, that stepper motors, that sensor we have used over PS sensor, that water sensor and H3 sensor for this particular project. So these are some of the cross-sectional view. And this is actually the major effect also. If we are going to dig it down up to like 40 mm, the temperature will drop from 25 to 26 degrees Celsius. So there is a huge drop. And due to the friction between the drill bit and the surface, it is going to have some heat generated onto the sides, which is also going to affect. And this is going to affect the drill bit, as there is a temperature transition and sudden change in temperature, which is going to increase the hardness of the surface, and it will decrease the toughness, which is going to result in the fatigue failure of the material. This is actually a vibrating unit that's shared by a TC linear motion motor. That is going to be a winch spring, then motor cables which are going to connect it, hammering unit and linear slider. And after analyzing that, if we are collecting a sample from the surface, there is actually a gear which is going to be connected with the drill. And connection with the drill, if we are lifting that sample up there will be some difficulty. And what we need to do, if we are connecting that component, what we are going to look at, there must be some hollow space in between that, so that that component or sample should be collected at that time. And these are actually the working which we have done. Simulation phase, prototyping. We are working on this one, prototyping, and at then we are looking for the mechanism design, which is going to analyze what will be the motion, what will be the RPM, power requirement, and what are the data set we are giving from the sensor. So these are actually the failure which will be taken into account while that testing. First one is the mechanical failure. As I have already discussed, due to temperature distribution, there must be stress generation. If we are taking that particular component, let us take that in Japan, they have taken it as approx 2 meters. And if we are going to decrease the diameter, it will increase the buckling. It means that the shaft is going to buckle from the middle, and it will affect the shaft and it will be destroyed. So mechanical failure, then we are going to have the electronic failure, like on circuit board. If we are going to have more power, it is going to have a short circuit. Other components failure, and at the end, this is going to be the signal failure. While communicating with the rover or while communicating with that satellite, if there is some miscommunication, that is going to be called as a signal failure. And these are actually a design engineer. These are the components or parameters I was looking at. So first one is stresses due to moon soil drill interaction. Strain, so due to that stress, there must be some strains onto the component. Torque required to for the drilling mode. Then power requirement, and at that what amount of drilling or what amount of volume we are getting while drilling per that time. At that other hand side, we are having temperature variation due to increase in depth. Second was in heat generation due to the interaction or friction between the surfaces. And third one is component heat generation and heat dissipation. While the components are in work, there must be some heat generation. So it is going to be like H equals to I square RT. That is going to be heat generation onto the component. That should be dissipated at a particular time, so that there must be not high heats or high temperature onto the inside, which is going to have the loosen of the component or failure of the components. So these are some of the SolidWorks simulations I used to do. These are actually the units which we have considered, like hammering unit. What are the components? Like linear motion of that motor. There is actually a bouncing spring, the Maxon motor, and the MF cam. And all these components are connected together. It is going to be a hammering unit, which is going to generate the hammering force onto the drill in case of MST. So these are hammering platforms, spraying motor cables, which are going to connect that motor with the hardware or the PCB. Second one is electronic unit. First one is antenna. Second one is free rotating device, as there must be motion onto the component, so it should be freely that rotated. As we look at the diagram, so if we are looking at the diagram, so sensor units are over here in this. So there is a free space in between that. These are going to be the connections or the sensors. This is going to be GPS, electronic computer, and all the other stuff, which is going to be over here. And this should be freely movable. And if we are connecting sensors with that cables and wires, it should be freely rotated. This is one of the important thing. First one is gear. So as we know that gear is going to have a hard surface. So hard surface, that there must be no wear while in working condition. So due to temperature variation, we need to protect, like if we are going to have the temperature variation, the hardness of the material is going to have some shattering of the gear, stepper motors and the motor cable which are going to connect, and handle of the rover and free rotating leveling device. So overall, what we are looking at in the design phase as a mechanical engineer, we are focusing on these parameters. So how we can solve and how we can rectify these, and by simulations, like we have did simulations in ANSYS. I'm looking in COMSOL also. So what are the heat generation onto the component? What are the parameters and what should be the material selection? At the end, one of the important major thing is material selection. While selecting a material for a component, it should be like whatever the stresses are generated, it should have high strength as compared to the strength generated. Like if we are looking up that car, if we are looking for design of a car, if we are choosing a hard material, it is going to shatter down in just an impact. So we need a material which should have high toughness, which will absorb that, the strength or impact, and it should distribute over the surface. So selection of material is one of the important parameter which we have already did. So, and second one is the thermal stresses which we are going to generate. It means that how we can handle that temperature variation onto the surface, and there is expansion and contraction of the material, how we can handle that particular also in the same time. So we can have longer drill or incubation onto the material. So these are the sensing unit, pH, water sensor and sensor. So these are the current projects TC has already shared with us. So this is actually the laser based that activation. And this is actually he has shared due to that magnetic charge particles, how we are going to collect. So we are focusing on just SPS1 and that moon sensing drill. And for that SPS1, we have already published paper in Delhi, I think 2 days back. So it was there in SPS1. So now we are focusing on SPS1 sample collection for and pebble collection, and then we can go for the MST. Thank you. Yes, sir. Yes, sir. So mass limitation, as VC sir said, it is approx less than 500 grams, and power consumption should be approx 20-25 watt. So actually we are getting approx 50 watt, and it should be less than 25 watts, so that we can have that other components also working at the same time.
Second thing in the MSD,
Yes, sir.
EMC part you did not mention.
Yes, sir. Okay, okay. This one I think.
Number one.
Yes, sir. This one. So actually, the use of helium-3 is actually, helium-3 is used for nuclear fusion. So that will be useful while we are traveling to Mars. So we can use it as a fuel. And this is also used for power generation also. Fusion is one of the most that highlighted topic in today's time. Actually, nuclear fusion is one of the best one. So actually, helium-3 is useful while generating a power, and we can also use it as a fuel. And that is actually available on the moon surface, and this is due to that radiation which is going to come onto the surface. And
I will explain this part.
yes,
So, EMC comes to solar wind.
yes,
It reaches moon surface because there is no atmosphere to stop it. But on Earth it doesn't reach.
yeah.
So helium-3 is embedded into the regolith of the moon. And if we detect it and we can mine it, it becomes source of energy not only on the moon, but as you said, to launch other space missions.
Yes, it will be helpful. Okay, sir. Thank you. Yes, sir. Yes. Yes, yes, sir. Actually, what we are looking for that if it's okay. So actually, if we are having drilling composition, so there is heat generation onto the site, and we can also heat that particular drill at the same time, so that will have conduction and even distribution of the temperature. So we are looking for that one also. So there are some other parameter we will. Actually, what we are looking for that if we are going to generate some amount of heat and we can convert it into temperature onto the drill bit. So actually on the outside, there will be contact between the surface and the drill bit, which is going to have the variation of temperature onto the drill bit, which will be contraction and extension. So that friction is also going to generate some heat for us, and we can heat up that particular drill also so that there is a change in temperature. It should be evenly distributed onto the drill, which we are looking for that analysis in simulation in ANSYS also. What we are looking for. Yes, sir. Surface temperature approx, I think, is 60 or something. It is going to be approx 60. We are looking for the bottom temperature. What we are looking for, that that 10 centimeter spacing of that layer, which is going to have a same temperature like -20 degree, -10 degree, -10, and then we are going to supply some amount of charge which is going to distribute. It is? It's not going to be one time. No. It is not going to one time. It will be like continuous formation. Yes, then we will take it out and that will be sample collector on it. Yes, sir. Thank you.
Thank you, Mr. Dinesh, for your enlightening us on the works that are going on in DYPIU. Now, I would like to welcome Dr. Richter Lutz, who is joining us online.
Yes, I hear you loud and clear. I hope you can see me and you can hear me okay?
Yes. Yes, if you give me a minute to introduce you.
Of course.
Yes, thank you. All right. So, sure. After the introduction, I'll rotate it. Yes, okay. So it's an absolute honor to introduce a veteran in planetary exploration and space robotics, Dr. Richter Lutz. With over 25 years of pioneering experience, Dr. Richter has made significant contributions to planetary missions led by ESA, NASA, and JAXA. This expertise has been central to some of the most ambitious missions in modern space history, including ESA's Rosetta Comet Rendezvous, the Mars Express mission with the Beagle 2 lander, and NASA's Mars exploration rovers, which operated far beyond their expected lifespans over 14 years on the Martian surface. Dr. Richter also contributed to Japanese Hayabusa 2 asteroid sample return mission, particularly through the mascot hopping robot, developed in collaboration with European partners and deployed on the asteroid Ryugu. His work in mobility and sampling systems is equally remarkable. He played key roles in the development of the ExoMars rover's mobility system and wheel design, as well as the sample handling system, technologies critical to the success of ESA's Mars mission. He has also been deeply involved in instrument pre-development for upcoming lunar missions, including an instrumented short drill and a LIBS laser spectrometer. Aimed to detect volatiles in lunar regolith. Notably, this collaboration extends to China's Yutu-2 and Zhurong rovers, analyzing soil mechanics from both the Moon and Mars. Currently, Dr. Richter serves as president of the International Society of Terrain Vehicle Systems, a leading global organization in terra mechanics and essential field for planetary rover mobility and exploration. He is also active in shaping the emerging lunar economy, and in 2022, he founded Terra Nova Industries, where he serves as president. Today, he will share insights from wealth of experience from Mars to Moon, terra mechanics, sampling tools, and rover mobility, a topic he has not only studied but helped shape. Please join me in welcoming Dr. Richter Lutz, for his interesting talk on the topic. Thank you.
Thanks very much for this introduction. That was very elaborate. And yeah, maybe yeah, humbled yeah, to be speaking at the symposium. Yes, I would have preferred to be there in person, but it didn't work out this time, and I'm looking forward to coming and sometime later this year. Let me share the screen. I hope you can see the title slide. Okay. Yep. I will go to full screen mode. Is it visible? Is it fine?
Not yet. Full screen is not done.
Can you see the screen this way?
We are not able to see the full screen. We can see the, maybe you need to share the entire desktop or something.
I can try that. Yes, give me a second. Because this we need to sort out first.
Share the entire screen, entire desktop or entire screen.
Yeah, the entire screen. Let's get it. I'm not so familiar with the
Google Meet.
with the Google Meet. I don't need.
Yeah, now it is
I
okay.
don't use it so
Now,
often.
now you can share.
Is it better? Can you see the title slide?
Can you go to full presentation slideshow? Yeah, now it is fine, perfectly fine.
Yeah, fine. Okay. Right. Yes, I will give some overview about, let's say, planetary and lunar surface robotics. And let's say, yeah, I'll be reviewing some aspects of in this discipline. So it's not only the design, but it's also the modeling, aerodynamics side of it. So related to sampling systems, drilling, scooping systems, and mobility on the surfaces of other objects outside the Earth. Because what is involved, several disciplines are involved, and Dinesh Kumar, who was speaking just ahead of me, I think gave a nice overview already of, let's say, the basic topics that are involved. And I like to boil it down, let's say, three disciplines that have to come together for planetary lunar surface robotics. So one is certainly electromechanical systems, because we're talking about actuated degrees of freedom for mobility and sampling. And then there is the interaction with the terrain material, so soil-machine interaction or rock-machine interaction, which is aeromechanics. And then autonomy, because most planetary lunar missions, it's difficult, if not impossible, to real-time remote control. So the systems have to have a certain set of sensors and electronics and software to be acting autonomously to some extent. And things can go wrong on such missions, as has been shown by missions of recent years. For example, the Mars exploration rovers, MER. This was a NASA project with 2 rovers on Mars in different places that were carefully selected to document the influence of ancient liquid water at the local materials. I was involved in that mission as a science team member. And so I was able to experience firsthand what was happening. The mission lasted for over 10 years, later, but embedding was something that happened a few times on both rovers. So the rovers getting stuck in relatively soft soil. Mostly it was possible to extricate the elements again, assisted by careful testing on the ground, as you see right. With a full-scale test rover to replicate the situation, but in one instance, not possible to recover the rover affected in the top right, artificial representation with real images in the background, because it could not be free, liberated, or executed anymore, and it was a mission ending event. So what are unique aspects with surface vehicles on other worlds? Of course, mobility, terrain hazards, autonomy, but also one aspect that's often overlooked, let's say, is the need to collapse, to stow such rovers for their transport to the moon or other planets, to fit into the respective lander spacecraft. So depending on the mission, depending on the accommodation, the vehicle may have to be designed from day one before we do it in a very efficient manner. And what you see here, some of the pictures are the Mars exploration rovers. So one of them shown folded as the lander tetrahedral structure was closed for flight on the ground. See, the six-wheeled vehicle looks very much different from what it looked like on the surface of Mars in the deployed state. Also, the Curiosity and Perseverance rovers, one of them shown on the bottom left, were designed for efficient storage in the landed envelope. So this is often overlooked and is a unique aspect of Earth. And then the autonomy right is necessitated by the common absence of real-time remote control. Lunar missions can be an exception to this, especially Mars. No continuous visibility from Earth to the surface of Mars, around its axis, so we have relay orbitals around Mars, but they cannot support like end-pipe communication, so you can upload commands to the Earth, and then autonomously go to activities also for mobility with autonomous hazard avoidance. Some mission examples of rovers, or design examples as well. What you see here is like a famous Akurdi six-wheel suspension of Mars rovers. Great for rough terrain, great for negotiating
services, and it was turned into the design of 3 sizes of Mars rovers by the US, by the JPL, of vastly different masses, from 10 kilograms to 180 and then to 1,000 kilograms, but it's always the same type of 6-wheeled passive suspension. Only the wheels getting bigger, the structure getting bigger. The ground pressure stays approximately the same. And as I mentioned, the MER Mars rover mission of NASA JPL was a twin spacecraft, twin rover mission, launched in 2003. And the program was completed 16 years later officially, when the second of the 2 rovers succumbed, let's say, to a global dust storm on Mars, which was mission ending. Spirit had died, let's say, after it got stuck a few years before that. But they were designed for just 3 months on the surface of Mars, and they lasted years. And for the scientists on the ground, including me, it was great because we could do a lot of geology, a lot of terrain studies, do strategic investigations, and understand the history of water in the distant past at those 2 landing sites on Mars. I will not speak about results of that mission now, because it would be too much to talk about, but it was clearly established by both vehicles at both landing sites that minerals were on the one hand deposited in liquid water, and at the other side there was alteration of basaltic minerals by episodic water influences and effects. And then the next bigger US Mars rover was Curiosity, which is still in operation today after landing in 2012 on Mars. It's a long-lived design with a nuclear power source. So rather than solar powered like Spirit and Opportunity were. So this design has no issues with global dust storms on Mars where the sky gets dark and other effects occur. So this is a design for longevity. Like Perseverance, which was launched several years after Curiosity, part of a multinational Mars sample return campaign. So both long-lived vehicles. China landed successfully on Mars with its Tianwen-1 planetary mission, its first real planetary mission. And the mission was successful, so it was a Mars orbiter, Mars lander, and Mars rover. It did some great science. The rover was a little bit bigger than the MER rover from NASA, a little bit bigger than Spirit and Opportunity. The suspension was kind of clever because it was hybrid, as it's called. So not only a 6-wheel passive suspension, but with active elements. You see it in the top right diagram where arms of the suspension can be actively moved and raised to help free the rover should it become stuck, but this was not necessary during the mission. And some nice things were done, like you see the image in the center. The rover dropped at one point a camera module onto the surface with wireless data transmission, and it took images of the rover and the lander in one picture. So this was kind of unique. So this is not a computer generated view, but it's a real image. Also, China was extremely successful with lunar missions over the past 10 plus years. It's part of the long-range program of it's called Chang'e. There were 2 lunar orbiters starting in 2007. And then the first soft lander with the rover in 2013. And then the second soft lander with the rover going to the far side of the moon in 2019. And since then, there have been sample return missions by China to the moon, Chang'e 5 and 6, where Chang'e 6 again on the far side. And the next missions are under development, Chang'e 7 and Chang'e 8. And then other actors entered the lunar, let's say, exploration arena. India with Chandrayaan 3, we heard about that already, successfully landing on the moon 2 years ago, and Japan with SLIM, which was a JAXA, Japanese Space Agency, a technology demonstration on the moon for pinpoint landing, which also was successful, and which carried micro robots that also imaged the lander, for instance, after landing. And anyway, we are witnessing many commercial lunar initiatives these days, as most of you will be aware. So commercial companies going to the moon, like in Japan, iSpace, their second mission is now in lunar orbit and preparing to land about 3 to 4 weeks from now. And then many actors are working on lunar rovers, commercial ones and institutional ones. And in the US, a lot of these activities are still funded by NASA partially, and then along with that by commercial customers paying for payloads to be taken to the moon. And at the same time, crewed lunar rovers are in development. Like in the US, it's called the Lunar Terrain Vehicle. For the point in time when astronauts again will be landing on the moon. And in the US, it's like a competitive process. 3 companies are doing studies right now, and one will finally be selected. So as you see, there's a lot of activity. We are looking at many rover projects in particular, and landers to get the rovers there, and the crewed missions and then uncrewed missions. Now, to successfully design a rover mobility system for a rover, Several aspects need to be considered, and I was going to emphasize that over the next few slides. So one aspect is ground pressure that's illustrated on this slide. So you need to design, let's say, your wheels, or if it were to be tracks, to have a large enough surface contact area with the terrain to keep the ground pressure relatively low, because otherwise you will have excessive sinkage in soil. And there is like an empirical diagram shown in the top left, which illustrates that for higher ground pressure, the probability of getting stuck goes up. So the probability of a no-go, let's say, mobility situation in soils. And it also did happen on Mars, as I was mentioning already. And you see in the bottom left view, that's a view from Spirit at its final resting place, where it was impossible to recover the rover. And the other aspect for successful rover designs is related to the suspension. And the suspension is related to the roughness of the terrain to be handled, to be survived, to be negotiated by the vehicle. And on Earth, we see some clever solutions like in logging vehicles, see here on the top left, the articulated vehicle solution where the body is split into several elements, several boxes, let's say, which are connected with hinges, passive joints. Also this Pavesi articulated vehicle at the bottom left. In the planetary and lunar world, articulated vehicles have been proposed, but so far not sent on a mission. For instance, the Marsocot of the Soviet Union is a famous example that was intended for Mars. So a body split into several segments, large conical wheels, basically no ground clearance, but the rover just passively, because of the split structure with joints, is passively able to follow rough terrain. In the US, a different approach was taken with the rocker bogie, shown here again, which, let's say, allows to have a single rover body box, but resorts to, let's say, a clever suspension to allow the ground contour following, while limiting the tilt of the rover body. And when designing a rover, yes, some trade-offs need to be made. If you want to maximize the payload to be carried on the vehicle, then you have to make compromises in let's say the mass devoted to the chassis, to the suspension, so the mobility performance will be somewhat compromised. Or if you want to have a highly mobile, resilient rover, then you will have to make some sacrifices in mass of the instrumentation, mass of payload to be carried. Some of that can be offset by clever autonomy to identify hazards, soft soil or roughness in the terrain, but still there are certainly some compromises to be made. And a successful design, let's say, for planetary rovers, also characterized by, let's say, some performance metrics. The data shown here are from the MER-B Mars rover, also called Opportunity, of the NASA MER mission. And you see here the estimated wheel slip or rover slip as a function of time. So plotted here is the days on Mars since landing. So just a portion of the whole surface life of Opportunity, spanning around 600 Mars days, about 2 Earth years or so. And you see that the slip was typically less than 20%, which is great, which is indicative of a good design. Only occasionally did the slip go up when like ripples were crossed, which are small sand dunes. So that's important to consider also in the design to make sure that the performance on soil and in the terrain is acceptable. And this gets us to, let's say, the simulation and modeling of planetary rovers, because that's part of the design process. So for designing vehicles on other worlds, it's important to have a proper modeling up front to be able to say how many wheels should I have, how big should the wheels be, for instance, or do I want to use tracks, even as in the Japanese Lupex rover that's coming up. So that's where the discipline of planetary terra mechanics enters the equation, where the mechanical behavior of soil is considered under the action of the vehicle. And there are three major types of predictive models for this purpose to support the design. So empirical models, semi-empirical, and analytical. I'll run through these rather quickly. Empirical models. Right, these come from, let's say, terrestrial off-road vehicles, especially in the military. On Earth, there's a large database on mobility success and mobility performance of heavy vehicles, especially in the military, like tanks, armored vehicles. And it's possible to construct equations to predict, as a function of terrain properties, to predict the probability of not getting stuck, for instance. But again, if you know the terrain, so you need to have an idea of the physical properties of bearing strength, shear strength of the soil. And this on Earth is available by ground level measurements, for instance, using penetrometry. So you can do cone penetrometer measurements in the field, outside by a human, to plot the terrain strength. And then there are correlations with the mobility performance as a function of the cone index, let's say. For instance, in the diagram on the bottom right, you see rated cone index, which is the proxy of terrain strength, and how that relates to the, let's say, number of passes of a vehicle over a certain terrain of that particular strength. As the strength goes up, so RCI number goes up, cone index number goes up. For higher RCI values, you have an increasing number of passes of wheels, let's say, trailing one another, or passes of several vehicles over the same terrain, with a good probability of not getting stuck. So these are empirical models. Another type of empirical models looks at the mean maximum pressure under a wheel or under a track. And this can be calculated to the equation shown here. What is entering in the equation? The weight of the vehicle, the number of wheels or number of axles, the dimension of the wheels, and also the deflection of the wheel, if it's yielding to some extent, like a flexible wheel. I give you some example. Let me, however, get the power supply to the laptop for a second. I give you I give you an example, which is an upcoming European lunar rover that's being studied right now. This is the project that I'm involved in over here in Europe. It's called the LPSR. Right now, different size versions are being considered, between 150 and 300 kilograms. But what you can do is, using this equation for the mean maximum pressure that I just showed, it's possible to play a little bit with the wheel dimensions and predict the ground pressure under the wheel for different sizes of this rover at lunar gravity. And you see some example calculations here shown here, where you see, okay, it's possible to find like wheel sizes for this four-wheeled rover that give a ground pressure under the wheel of between 10 and 25 kilopascals or so, which is great based on the experience from terrestrial vehicles, which is good to minimize the probability of immobilization, which is a good thing. Empirical models have also been used by let's say, by the Soviet Union for developing the lunar rovers more than 50 years ago. And they did a lot of tests with single wheels and with rover demonstrators to build like a database of mobility performance to then down select the final design. Semi-empirical models as part of rover design efforts, they are more physics-based because they consider stress distributions under a wheel or under a track of a tracked vehicle. So normal stress distributions and shear stress distributions. And these are basically calculated in such models for known soil properties. And the soil properties, the interaction parameters, as they're called, are determined by measurements using instruments called bevameters, which approximate the shape of the wheel by a flat plate. So or let's say the contact patch. The contact patch between the wheel and soil is approximated or simplified by the action of a flat plate that is loaded by the weight from the top and which experiences shear which is the case for a powered wheel of a rover where torque is applied. And this flat plate action on soil is simulated in this instrument called a bevameter, which performs either in the lab, such loading tests, or outside in the field. You see a field bevameter shown here on the left and the lab bevameter on the right. And this way it's possible to measure interaction parameters, which enter the equations to calculate the stress distributions under the wheels or under the tracks. And these models are very well, have a huge database on Earth for terrestrial vehicles. They were also, for the first time, they were applied to lunar rovers for the Apollo crewed lunar rover design to support the wheel design for the Apollo lunar roving vehicles in the early 1970s, late 1960s. Some pioneering work was done in that respect, and this type of model, which is not very complex, was successfully applied to help design the wheels for the Apollo crewed lunar rover. And the predictions from that model, which were used to support the design, were correlated with mission data based on, let's say, the measured energy consumption of the 3 Apollo rovers that were sent to the moon on the last 3 of the Apollo missions, where energy consumed from the batteries of the rover was plotted as a function of time and distance traveled. And this was correlated with the predictions from the semi-empirical model, and a very good match was achieved. And Regulus physical properties on the moon could be inferred from the mission data. In Europe, we also work with this type of model. I was involved with that a lot a number of years ago when we were here in Europe preparing for the ExoMars rover mobility system design. So basically, we also work with semi-empirical models. However, adapted them for much smaller wheel sizes and much smaller rover weights than was the case for the Apollo lunar rover. So dedicated modifications of this model had to be done to get to good correlation with single wheel measurements in the lab and rover system tests in the lab. And this was then applied, this type of model, to help design the wheels for the ExoMars rover. This was an activity also mentioned in the introduction that I was involved with a lot. We selected a metallic flexible wheel, and the choice of stiffness by design was based on predictive modeling using the so-called traction prediction model, which was a semi-empirical model to describe the wheel interaction with the soil as a function of soil properties, as a function of wheel parameters. In China, with their lunar rovers and their Mars rover, they also, this is maybe interesting, Chinese researchers also adopted semi-empirical models to support the design of the wheels and of the rovers. especially an interesting slip sinkage model was derived as part of that effort. And the designs confirm and the operations confirm that it was kind of successful. Or it was certainly fully successful. So the models can be considered as having been the right choice. Analytical models to support rover design and development. They are can be split over different approaches, like finite element modeling of the terrain deformation, or discrete element modeling, or variations of these. So these models are really effective at the micro scale. They are computationally, let's say, intensive, however. So if you want to couple them with like real-time simulations of rover mobility, that's computationally tough. FEM started to be used in terrain vehicle design in the 1990s, early 1990s, especially here in Germany, also in the US. And they were quite successful. However, the natural limitation is that the, let's say, the strain of the soil under action of the wheel cannot be too large. That's an inherent limitation of FEM. However, different approaches, variations of the FEM have been tried to also describe larger deformations of soil under the action of a driving wheel. And so this is one approach computationally that works with satisfaction, let's say, to support rover designs. More recent variations are MPM, that's the material point method, which is derived from finite element methods. And it's faster computationally, so that's a key advantage. And you see some example outputs from such work in figures here on this slide, where you can see stress distributions and displacements of soil under the action of a driving wheel. And then DEM is another class of analytical approach where you represent the soil by individual particles as more or less conforms to reality. So basically you have differential equations of motion for each of the particles, so how they move relative to one another. And to limit the computational effort, it is possible to represent the particles having a bigger size than would be the case in reality. And there is like a rule of thumb how much you can deviate, how much you can increase the particle size over the, let's say, the actual size in the real case for still representative results. The good thing about DEM is you can easily address also the effect of gravity on the soil behavior, because the strength of a soil bed is also affected by the local gravity level. So with reducing gravity, actually the strength decreases, the in situ strength, and so the bearing capacity is reduced, the shear strength is reduced, and all of this can be easily considered in DEM type models of the interaction between a tool or a wheel with the soil-like material. See some examples here where researchers, for instance, have looked at the slip sinkage phenomenon of wheels, and experiments could be very well reproduced by DEM modeling. It's also possible to increase the computational speed. It's possible to go to so-called coarse graining, which kind of averages the movement, the states, motion states of a group of particles. That's so-called coarse graining to make the computation faster of DEM type models. So the different predictive models to help with the design of rovers. And then during a mission, of course, you obtain some actual mobility performance data, and you would like to correlate your model with the actual performance. But this is not so easy, and not much work is available. I showed you the example for the Apollo rover, where energy consumption was used as a proxy to correlate the model, the predictive model. And usually there is a limitation in the sensors in the instrumentation. So lunar or planetary rovers, you're not able to have the suite of sensors in the flight hardware that you would like to have for comprehensive model validation because of limitations of such sensors in terms of the space environment, temperature extremes. Force and torque sensors are very hard to adapt to be working under harsh space conditions, for example. But there are new developments that can help with providing more insight into actual rover performance, such as real-time image processing on board of rovers that can allow to more accurately observe the sinkage of wheel in the soil to support model correlation. This is what I just alluded to a minute or so ago, the effect of gravity and how it relates to testing on Earth. So one thing is clear, gravity affects directly the weight of a rover. And if we go to the moon or to other bodies, there is a different gravity level, so it's lower than on Earth. And we need to factor that in for mobility testing. In India, for instance, for the Pragyan lunar rover testing, helium balloons were used to reduce the weight and allow mobility testing. And in China, that's the other example shown here, people work with an overhead suspension, which with controlled tension in real time to partially offload the weight of the rover. However, there's also an effect on the strength of the soil. So for the same bulk density, for the same compaction level of the soil, the strength of the soil bed at reduced gravity is lower than it would be at Earth gravity because the overburden pressure is simply reduced. And the magnitude of this difference depends on the amount of cohesion in soil. The more cohesion you have in the material, the less pronounced this effect of gravity is on the strength of the soil. For dry sand, cohesionless dry sand, the effect is the strongest. So there you really have to pay attention when doing mobility testing on Earth. This also relates to testing of excavation systems like are being considered for the moon, for instance. And the way around that is if you do parabolic flights in airplanes, for instance, to simulate lunar gravity or Martian gravity, you can do single wheel testing as shown here, with also the soil being at the right gravity level. And this was pioneered in the Soviet era when developing the Lunokhod rovers. They were the first to do such tests. And then like 10, 15 years ago, in Japan, similar activities followed, and more recently in Canada. Now, let me, as the final aspect of this talk, I was going to touch on sampling systems. Yes, this was mentioned by some of the speakers before me already, because some of us have already collaborated in this project, which was the Beagle 2 Mars lander. More than 20 years ago. This still counts today as the only European landing on Mars, where the lander survived all the way down to the ground. The lander didn't get to operate fully, however, because of a deployment issue, but the landing itself was fully successful and the lander survived the landing phases. And this lander was really subjected to tight mass and volume requirements. You get a sense of the size of the lander from the ground test model shown at the bottom left, with team members in the background. And there were some clever sampling devices on it. to feed samples to the analytical instruments inside the lander. So one was TC, one of the speakers this morning, is the inventor of the rock corer grinder on that mission with an articulated drill head like a chisel to chisel into rocks and capture the debris to be made available for analysis. The second tool was the mole that was mentioned also by TC. For subsurface soil sampling to be delivered to the analytical instrument in the lander. And the mole was kind of clever because it could not only move into the soil, but also hammer backwards to support the return to the surface and taking a sample by a mechanism in the front tip. And all of this was actuated by a single electric motor to operating two different senses of direction and an internal kinematic to change between the operating modes. Another, let's say, more widely used concept or solution to take soil samples is the scoop, or like the bucket excavator on Earth. So it's a scoop-like system that was used on Mars missions and also even on the Moon early on. And there are models here. Again, we're talking terramechanics. So because during the design, you have to know what forces have to be overcome for the excavation, for the sampling, for pulling the scoop through the soil. And also here, successful models are, let's say, semi-empirical plowing models from terrestrial applications that describe the resistive force to be overcome. And this you need, obviously, to size the actuators for an arm, let's say, that supports a scoop that has to pull the scoop through the soil to a certain excavation depth. And using such models, it was possible, for instance, to estimate the shear strength of soil on Mars. For instance, shown here are results from the Phoenix Mars mission, which was a single lander mission to Mars 15 years ago to go to a high latitude site on Mars. And team members used such a semi-empirical model to estimate cohesion and internal angle of friction from measured motor currents in the robotic arm during the scooping. In Europe, I mentioned the mobility system for this rover, ExoMars rover. I was involved in that. And then later on, I was involved in the sample handling system for the rover that sits inside the rover. It's part of the analytical laboratory. On the outside, there sits a drill to drill into regolith. This was developed by a company in Italy. And the drills are transferred into the rover, into the interior, where the samples are first crushed into a relatively fine powder, and then the powder is dispensed, is metered into ovens for the key instrument that analyzes the sample. And also there are viewing instruments like hyperspectral imagers, close-up imagers that look at the powder. And the science instruments, they have this requirement for a very fine powder, therefore the need to crush the sample to smaller grain sizes. The resulting mechanisms to do this job are quite massive. So overall mass of the sample handling system was is around 15 kilograms, spread over 4 distinct mechanisms that have to be secured until after landing on Mars. And this is the rock crusher, the crushing station flight model, which kind of is a jaw crusher to turn the unknown nature of the samples taken by the drill into fine powder, which is then collected and distributed to instruments. Right, and then for the Moon, where sampling systems are concerned and rovers are concerned, so I mentioned this earlier, we're looking at, let's say, a new era in lunar exploration with many more rovers, large and small, and many more landers. And and sampling systems, as pointed out. And rovers can be as large as a pressurized rover, shown here by JAXA in the center, which is the so-called Toyota Lunar Cruiser, a collaboration with the Toyota Motor Company, and then tiny rovers of just a few kilograms of mass. And okay, this we already talked about. And all of this is in context of, let's say, upcoming crewed lunar programs, where astronauts will again be sent to the moon. So there is an initiative. Let's say, led by the US. There is a so-called Artemis program to send astronauts back to the moon. And in parallel, China is leading an effort called the International Lunar Research Station, which also will send astronauts to the lunar surface. And we're looking at some sort of competition between these two programs, obviously. And let's see who will be first to, again, put people on the moon. And this will be in the south polar region of the moon, which is exciting for resource aspects. And so part of this effort will certainly be sample acquisition in various ways. So regolith scooping, drilling, and pebbles and collection of rocks, like also pointed out by Dinesh earlier, the talk before me. And some novel approaches have also been demonstrated recently on the moon, like using pressurized gas to assist in feeding regolith from the surface to instruments, or let's say for sample return. Right, so I'm almost at the end of my talk. I was going to highlight two promising instruments that were also mentioned in the introduction, actually. So one is instrumented drills, I believe, will be very important for uncrewed missions to the moon. And Dinesh before me described the moon sensing drill that we together actually are working on in a collaboration. Another type of instrumented drill is the LVS, or Lunar Volatile Scout, that was into prototype level here in Europe, which is a shallow drill to detect volatiles in the regolith of the moon with an attached mass spectrometer. And there was a parallel project funded by the European Union that's called Voila, which is a LIBS instrument, a laser-based instrument, as shown on the bottom right, to measure, to look for hydrogen and oxygen in the regolith of the moon. So related to the search for volatiles, but using a different technique. Right. So to sum up, so with the upcoming, or with the current new search in lunar missions, and then also further Mars missions, we're really looking at a lot of things to be solved and to be considered with regards to mobility of rovers and with regards to sampling systems. And part of these efforts certainly is modeling and simulation as part of the design activities. And this is where terra mechanics gets involved. So the science of interaction between a tool and geologic materials. And let's say the proper use of these predictive tools is important for successful designs. Yes, thank you for your attention.
Are there any questions? So if you can come here.
Yeah. We asked few questions, I would like, so if I can hear the answer. Hello, Lutz.
Yes.
Hello.
I hear you.
Yeah. This is Swapnil.
Yes.
Yeah. Lutz, this is Swapnil. Yeah,
Yes.
actually, we went to GLEX 2025. Unfortunately, you were not there. Uh, During the presentation, they raised few queries. So if I can get your stand on that, those queries.
Okay. Yes.
Actually, the SPS one, what we are proposing, soil paper sampler, what we have presented there. In that one,
Correct.
we have given the brass brush at the end. Brass brush.
Right. Yes.
Right? So one of the question from the audience was like, if we are going to clean the soil table samples, then the originality of that soil may going to be damaged. And in such a case, if you are going to do that, then how can we do the proper spectrometry of that sample if you are going to clean that sample? Because we are focusing on target sampling, that SPS one. So if you are
Yes.
if you are going to do the target sampling by cleaning the sample with the brass brush, then it may going to damage its originality. So what is your stand on
Right.
that?
Yes, good point. Let's say the brush, TC, correct me if I'm wrong, but in
Yeah.
SPS, the purpose of the brush is to clean off, let's say, to remove superficial particles like dust and soil that could be sitting on the surface of rocks. And this is like similar to cleaning brushes, revolving brushes that have been used on Mars missions, on Mars rover missions. So at the end of the robotic arm. So to make it short, it has the function of a cleaning brush. So to remove dust from the surface of rocks. So it would not actually contaminate, or it would not actually physically change the surface of the rock, just removing a portion of the adhering dust on the surface. That would be my take. TC, you want to add to it?
I think the brush is big of, the British brush is big of horse, brushing the hair of the horse is copper.
Okay.
I don't think any even with the spectrometer.
So is there mean like is that mean we are going to use the brass brush for the cobbles, means for the large rocks, not for the soil or small pebbles? Is it for only the large rock, or it is for soil as well? This is what I wanted to ask.
It's not for soil. It's not for soil because it's not part of a sampling system for soil, but it's really to clean off. I mean, it's to look at rocks.
Okay. We can have another meeting. Yeah, that's true. Thank you.
Just
Thank
to
you.
combine, it's combined functions. It's to combine several functions into a single tool, which is the SPS.
Okay, sure. Thanks.
I think, can I say something?
Yes.
I think the brush you're talking about is CCC. You mean the RAT brush, you know, of honeybee robotics is a copper brush. The copper brush is to remove the rind surface and the APX examination. But I don't think any interfere with the spectrometer. You know,
Correct. It doesn't alter. It does not change the composition.
There's no change. It's
correct.
The same. You know, we are using it in GCC, and now yesterday I suggested we use it in the cheese knife on the upper and lower surface of the sensor.
Thank you. Thank you.
Thank you very much, Professor Lutz, for introducing us to different efforts in sampling and mobility issues of planetary explorations. It is now my privilege to introduce the next speaker, Dr. Parameswaran Sreekumar, a prominent astrophysicist and science leader whose work has significantly advanced India's contribution to space science and planetary research. Dr. Sreekumar currently serves as professor and director of Manipal Center of Natural Sciences. Prior to this, he has held several key positions at Indian Space Research Organization, including the director of ISRO Space Science Program Office and was the principal scientist as Astrostat, India's first dedicated multi-wavelength space observatory. Over the years, Dr. Sreekumar has worked on critical aspects of high-energy astrophysics, instrumentation, and planetary science, and has contributed extensively to India's growth in planetary exploration agenda. His insights into the space environment, especially radiation exposure and particle interactions on planetary surface, are vital for both robotic and future human missions. Today, Dr. Sreekumar will be speaking on the subject of increasing relevance to in situ planetary missions, neutron radiation environment on planetary surfaces, relevance for surface studies. His talk will shed lights on understanding radiation patterns and neutron interactions is essential for both scientific observations and safety for equipment and astronauts. Please welcome along with me Dr. Sreekumar.
Good afternoon. Can you hear me?
Yes.
Yeah. Okay. Thank you. I'm really sorry that I couldn't be there in person because of some difficulties locally. However, we briefly present to you some new work we're now working on in the video using neutrons as probes for planetary studies. At a time some years ago when Prabhat and some of us were discussing about Chandrayaan-2 rover. This is way back actually. And then one program, we had some exciting thoughts. Some of which then are worked out. So such a meeting is certainly very beneficial in actually exploring future avenues where we can actually collaborate. So today I'm going to talk about this neutrons space, which I believe something that has been slightly ignored. So neutrons are not just about to scientists also. I have got a full screen at my end. You do one thing, you share it again at the entire desktop. Share the entire screen? Yeah. I'll try that. Entire screen is not being shared.
So when you're trying to share on the top, there'll be an option to change from in the sources. As soon as you press on share screen, there's an option. Yes, yes. Please choose entire screen.
Entire screen.
Yes, sir.
Share. As we do we probe the universe using photons, particles, and gravitational waves these days. And the photon, of course, we are very much used to in the electromagnetic spectrum from radio to gamma rays. But today I want to focus on these particles, in particular neutrons, which are neutral particles, which in principle are better than charged particles to study the universe because they're not affected by magnetic fields. But neutrons, unfortunately, can only be used for near-term studies like the sun, because neutrons are not stable. Free neutrons decay into protons and electrons and a neutrino in a matter of 880 or 900 seconds. However, it has interesting applications when you look at at planetary science as well. So the prime focus of today's discussion, I just want to say, is we want to look at this in the context of understanding neutrons from the sun, its origin and spectrum, and how it's connected to solar events like solar flares. And we are very familiar with solar flares, where you look at X-ray emission that rapidly rises and falls off in about 30 to an hour or so. However, there is no reason to believe that, and there are other reasons to believe, and from gamma ray data that suggests that flares could last for very long periods of time, hours. And one of the ways to study that would be through neutrons, but then studies of neutrons from flares have been limited, difficult, and requires a lot more work. Neutrons, however, from a planetary science point of view, has a very interesting, is a tracer for hydrogen-based compounds because of the close interaction of neutrons and protons. And so this is an emphasis for search for subsurface water and ice, and that has been successfully attempted at Mars and as well as on the Moon with regard to search for water ice below the surface. And the third point would be that neutrons are really critical components of radiation that's harmful to humans, and with more humans going to be in space, there's a greater need to understand them, because the radiation effects of neutrons in biology on biological material is many, many times that from, say, protons and gamma rays. So that is a concern that we need to know in future, which means we need to understand all sources of production of neutrons in space. So production processes include, typically, in this case, I'm now looking at the sun itself as a source of neutrons. And the sun's surface, when accelerated particles, in particular protons, interact with the atmosphere and here the photosphere and the chromosphere, which are the more dense regions of the solar atmosphere, you can produce neutrons, various combinations of alphas and hydrogen, helium, and heavies. Neutrons are also produced, and these protons can also come from the galactic cosmic rays, but also come from acceleration process of the sun, like reconnection events connected to flares. And on the case of planetary systems, you actually have the galactic cosmic rays interacting with surfaces and atmospheres of planets, which produce neutrons below the surface in the atmosphere. So someone standing on the surface, or a rover or an experiment on the surface of a planet, would be subject to these neutrons from top and bottom. These are detected often directly. From the solar, neutrons can be detected directly, provided they are higher energies. The low energy neutrons are fully absorbed, often decay because their lifetimes are not long enough. But energetic neutrons can actually be measured using ground-based neutron detectors, which has been going for more than 50, 60 years. And if you're closer to the sun, you can use spacecrafts to study low-energy neutrons. And some of the indirect signatures of the presence of neutrons would be that neutrons are absorbed by protons to produce a gamma ray at 2.2 MeV. These neutron capture lines are detectable by gamma ray instruments. And you can also see indirectly the protons arising with the decay of neutrons in flight. These were initially discovered in the 1980s, people studying solar flares. Subsequently, and many other solar missions dedicated to look at the sun, and including today, the Fermi satellite that has been studying gamma rays for the last, now, I don't know, 17 years or so, has had many occasions to see gamma rays coming from the sun. But direct detection of neutrons is not straightforward because of the difficulty in actually distinguishing gamma ray and neutron events. The Comptel experiment on Compton Gamma Ray Observatory was unique in its ability to distinguish neutrons and gamma rays. However, the presence of these line emissions, etc., suggests these are arising from ion acceleration. And a key thing when we try to observe from Earth would be to look at the arrival time of neutrons and to study and invert that into a spectrum of neutrons. The spectrum that you measure at Earth needs to be converted back to a spectrum that started from the sun. And typically you find that such neutrons are produced in extreme flares, X-class flares, flares that are extreme. And often these are more prevalent during the solar maximum. Remember, the sun has a cycle of 11 years, and during solar max, we expect to see a lot more X-class flares. So here's a simple calculation that actually shows that if I take a measure blue, a spectrum is a power law spectrum, number of neutrons on the y-axis versus energy. And now assume that there is neutrons are decaying, and given the fact that high energy neutrons travel fast, and hence they will reach before the decay, you see that somewhere around 100 MeV or so, beyond 100 MeV, the spectrum that you measure at Earth is roughly identical to what you would expect what is at the sun itself. However, lower energies you underestimate substantially because of the fact that much of the neutrons are getting absorbed from the. So the green is what we think is the spectrum that started from the sun, but when it gets to Earth, you see the blue spectral line. So there is a need to really correct for the measured neutron spectrum at Earth. And this is where I suggested that the study of neutrons tells you something about the nature of particle acceleration as not being instantaneous or impulsive, but rather it's also possible that they actually extend over a long period of time, as shown by this black curve. The flare happens at some T0, which is detected. It should have been closer to this peak, sorry. But X-rays are detected within 8.5 minutes. And then you have this wait for neutron to come. 100 MeV neutron reaches Earth at about 20 minutes or so. And if I then count the number of neutrons as a function of time, at small intervals of time, I can, in principle, invert that to get a spectrum that starts from the Earth, from the sun. So here is an arrival time distribution as a function of energy for neutrons, and you can invert that and actually convert that into number of neutrons with, as a based on this distribution, you can actually then convert it back to the spectrum of the sun, provided this is impulsive event. That is where you are directly saying the arrival time is simply dependent upon the energy of the particle. If it is not an impulsive event, it's actually a gradual event, then you need to really measure the energy of the neutrons. And that brings you the challenge of making detectors that can measure energy. This is, of course, a very simplistic analysis or complex analysis where the spectrum is not a simple power law. You actually see this will take a little bit more work. So I leave this at that point and then come back to this discussion about neutron production at planetary surfaces, where cosmic rays constantly bombarding planetary surfaces. On the moon, there's no atmosphere. The regolith acts as a medium where these cosmic protons produce various secondaries, and one of the secondaries that emerges back from the surface would be neutrons and energetic neutrons, which are scattering off the regolith constituents. So the study of these neutrons are interesting in itself, but primary purpose of studying them on the moon would be to really ask this question: those neutrons that are coming back from below the surface, that spectrum. And that is, in other words, neutrons at low energy, very low energy, and high energy. That ratio of neutrons, in particular the low to high, could be impacted if there is presence of water. Water, which has a lot of protons, would absorb neutrons, low energy neutrons. And so you would see a change in the neutron flux at low energies if there is water in the regolith. And so this has been used to look for neutrons both from the orbit, using the LRO, many other missions. It's been similar thing has been done from Mars Odyssey mission by with Fano and team. And so that is experiment. And now on rovers, like the rover on Mars and Curiosity, there are experiments that are meant to look for this difference in neutron flux at low energy, so rising from the presence of water ice below the surface. So we do this through certain simulations. Here I'm showing some simulations using a tool called Fluka. You actually allow the protons to fall onto the surface. You break the surface into various layers to address compositional variation, density variation, as well as to really change the amount of water in it. And then you look at how neutrons are produced in these layers, and then you look how many, track them and ask how many of them show up onto the surface. And then that is used to really address, can we measure the presence of, or detect the presence of water ice below the surface. What you see here in blue are systems where you actually have the spectrum is shown at low energy, medium energy, and high energy. And high energies, you see the spectrum doesn't change very much. And this particular lower right plot, what you see is the fact that a lot of this happens, these production of these neutrons below the surface happens, say at 20 centimeters to a meter. So up to a meter or so, one can actually use this technique to search for water. The searching techniques are, again, a little difficult. Neutron detection is not easy for a space payload. So the technique that's often used is to really, if you want to measure medium energy neutrons, you actually lower their energy through a moderation process. You actually slow down the neutrons, and then they are measured as thermal neutrons, because thermal neutrons can be captured in helium-3, in barium boron 10 compounds, lithium hydride, and so on. If you really want to study fast neutrons or high energy neutrons, then you really have to use them using scintillators like liquid scintillators Ne213, and use some sophisticated techniques like pulse shape discrimination to really separate neutrons from gamma rays. So there is a approach to really doing this, and that's an exercise we're now involved in. We try to look for possible designs for the future Mars rover, where you're thinking of this as a cartoon of such a design, where you have fiber bundles where fibers of lithium hydride embedded in a scintillator are stacked with a layer of absorber in between, boron carbide, and at the top layer you'll actually measure the thermal plus epithermal, the medium and the low energy. The bottom one, the medium energies are all the low energies are fully absorbed by the B4C, and you're left with only the epithermal. So between the two, you can then distinguish between thermal and epithermal. And that difference arising whenever there is water present on the surface of Moon or surface measurements can then be used as a tracer for water ice on the planetary surface, subsurface. So it primarily relies on, in this case, lithium absorbs a neutron, produces a helium-4 and an alpha particle and a triton, and which quickly release energy, and you can actually see the scintillations. In the simulation, we were able to show that at the end of the fiber, you're actually seeing this light, and that can be used as to track the presence of the relative flux of the low and high energy neutrons, and which in turn suggests the presence of water ice. So as I mentioned earlier, there have been efforts in the past. So this is nothing new. This is traditional instrumentation as well. But the challenge often has been to make it compact and make it, in some cases, the ability to look at even fast neutrons, directly measuring fast neutrons as a scaling of the spectrum, which then allows you to really distinguish the absorption arising from the presence of water ice. Here is count rate of neutrons measured by the DAN experiment, which is actually a dynamic albedo of neutrons. It's an active instrument which actually carries a neutron source, and you can actually see the change in the neutron counts as a function of time. And so that's the experiment we're now involved in. We're trying to really come up with a custom design that is easy to fabricate, to test, to really see if we can actually do both thermal, epithermal, and possible a little bit of the fast neutron flux measurement from a rover. And our challenge is, of course, is trying to make it compact, low mass, low power, because this has to be a rover. So that is going on. In the last few minutes, I just want to sort of say we're also looking at this effect of solar neutrons or neutron environment for humans in space. And so we've been looking at the higher data from an experiment inside the International Space Station that measures neutrons. We included neutron flux arising from protons interacting with the wall of the space station, cosmic rays interacting with the wall of the space station, and during flares, solar flares. And so we now reached a phase where we're able to reproduce using these calculations the observed. So on the bottom left, what you see is an observed curve where the red points indicate the counting rate seen, about 4 or 5 counts per second inside the space station. This is from 2023 data that the Marshall Space Flight Center had actually flown. And calculations are starting to show that we're getting close to 2.5, which is for such calculations very close to 5. So we are in the ballpark, but we still have some work to do on that issue. So in future, what we intend to do is to really work jointly with ISRO and maybe members of our Tata Institute team in UTI to develop lithium fiber-based or gadolinium included simulators to really build a neutron detector, refine these multicolor calculations to improve the instrument, and then look for a future opportunity to piggyback and land a rover mission in sometime in the future. So I'll stop there. Thank you. This is the team that I have. Just want to indicate we have a team, a postdoctoral fellow, Dr. Ashwini, works on FLUCA simulations. Narendranath, she's an MSc project student, just writing up a project report. Ahmed was with us as a PDF for some time from Turkey, who worked on the Gian simulations, and Dr. P.N. Bhatt has been from the University of Alabama, who is part of the ISS experiment, which kindly shared some limited data on the ISS. And so thank you, and questions, I'll answer that. Yeah.
Any questions? Well, looks like there are no questions. Thank you, Sreekumar, for
Thank
joining
you.
us.
Sure. Yeah.
Thank you, Dr. Sreekumar, for your insightful talk on the radiation on the environment of the planetary surfaces. Now, I would like to welcome Professor Prabhat Ranjan all over again to sum up on the experiences with in situ exploration of the moon, of his second part of his talk. Sorry, we had to split his talk into two parts. He's also one of the hosts, so he would end up with talking about his experiences all over again and take us back to his work.
Actually, it's interesting that Sreekumar is here, because this particular presentation was something happened that with the email that came from him in 2010. I've kept that presentation, the old presentation is still there, it's a 15 years presentation. And it's also interesting to see that Sreekumar working on about neutrons. So I'm also working on neutron generator right now, but that's a different thing. Now this one is something that happened in 2010 with an email that I received from Dr. Sreekumar. And mission plans were changing, so this I've left it because this, oh, it's not being seen. Just hold on a second. Yeah. Okay. Yeah. Okay. So this work was done 15 years back, but most of the things here are still relevant. That shows that how much slow progress has been there in this area. But this all happened because of change of Chandrayaan-2 plans that happened in 2010. In fact, it happened over a couple of years' time. And I will not go into the detailed part. As I talked in the morning, we're already working on some projects related to wireless sensor network for detecting water and for seismic observations. But we were told that you have to develop a system as per Dr. Sreekumar's email and then had further discussion. And the mission was to be launched in 2 years' time only, 2012. Any of these missions is very difficult, even 8 or 10 years are very less. So I had to try to get help from anybody else in the world possible. And ISRO suggested us TC's name and his partner Sean Whitehead. They were working together on many interesting projects. Dr. Tom Pike used to work at Jet Propulsion Lab of NASA. And then he had moved to Imperial College London. He was working on seismic sensors. I was already connected to him. And Dr. Tom George, my friend and apartment were from US. He was head of MEMS group division of Jet Propulsion Lab. Then he had moved out later. I will leave out this part. The purpose that I was given about 1 month time to prepare a proposal, which was going to do geophysical and geochemical measurements of surface and subsurface near the landing area in the polar region of Moon. So as we know, India was targeting the polar region of the Moon, and we landed successfully Chandrayaan-3. The system was to do all the things needed in an integrated system. And I'll show you, the top level objective was to carry out scientific experiments to better understanding of lunar resources and lunar environments for future space exploration. The task, especially the geochemical analysis was one, polar volatile measurements were there, thermal and electrical properties were evaluated, a study of lunar shallow surface structure, and collect data for a global seismic survey. So these were the tasks that were defined. And all of this had to be done an integrated payload. The idea from ISRO was that you optimize all the different systems. There may be 6 subsystems. Rather than designing all of them separately, make an integrated design so you can integrate all of them together in a very optimized way. The task that was given to me was that you need not do all the development, but you have to put everything together, and it comes a single payload from you. They told me that it will be like Prabhat Ranjan's payload. Okay. And what meant that right from the early stage, if the systems are being planned together, the optimization will be there in terms of power supply requirements, mass, and so on. As TC has been emphasizing time and again, that 1.5 pound or 2 pounds is very important rather than doing 20 pounds. So the mass and the power requirements are very, very critical. Okay. So let me skip the details. Requirements were that you could do deep, no deep drilling required, but 50 centimeter was given the requirement to should be able to drill 50 centimeters. And for this, we have already talked about Beagle 2 and ultrasonic drill. These are the 2 technologies I had considered. Beagle 2 was already, the team was associated with us, TC and Sean Whitehead. I also looked at also. So you have to drill the surface with only 20 watts of power available. And mass also small. Normal, any drilling machine that you have which drills few inches is 1500 to 2000 watts. Here you're getting 20 watts because at that time Chandrayaan-2 had 40 watts of solar panel. They told me you can take half of it and half they have to use for rover operation. So 20 watts and you have to go 50 centimeters, something like this. You can imagine that was the task. So instead of trying to use traditional techniques, we looked at the alternates. So Beagle 2 was one example that has been talked about many times. I'll not go into that. Other was ultrasonic drilling. Both of these we had considered. Effectively, what we do is that instead of continuous drilling, you charge a capacitor to high voltage, and it's called impact hammering. So just like as a human being, we lift and hammer and then impact. Same thing, you charge something and then hammer. And again, wait for some time to charge. So it will not very fast, but it will do the task within that. We had considered both of these, but more the Beagle 2 design we had preferred. And in this itself, we had also made a provision for volatile detector. So that was shown here in the yellow thing. And so we could measure what is coming out by heating the things, and volatile we could sense that. Other option that was talked about was the surface rock preparation. This was an optional thing. Again, I'm not going to go into more details that it has been talked about. So this was the design that was used in Beagle 2. TC is sitting here, so this design was part of that. There was another one that rat pack we had considered. So then we had geochemical measurements were there. And for this, we wanted to measure major rock forming elements like oxygen, magnesium, and so on. And we could measure through X-ray fluorescence spectroscopy. But we had few options for these. The three options that were there was alpha particle X-ray spectrometer. This was being already developed at Physical Research Laboratory. Beagle 2 had the X-ray spectrometer, and there was another technique called electron dispersive X-ray spectrometer. Beagle 2, if I remember the mass of this correctly, was only 75 grams. So, a very small mass that was used. What I had found that the diode that was used could have been changed by another diode, which was another detector, which was a better one at that time. As 15 years passed, so it might be even better options might be available. Okay. So, a very small mass was there. And then we had to monitor volatile part. We had multiple options in this also. This was, for example, a miniature quadruple mass spectrometer, very small. You can see compared to the coin size. This is the option of tunable diode laser. This is ion trap as mass spectrometer. So then we defined certain baseline instruments based on all these options. Tuned diode laser work was already going on. So we wanted to, this I have already talked about, so let me leave this part. Okay, now let me show you this part of design which I had not shown. So this was a seismic sensor. It's like a cricket wicket that you hammer inside the surface. That's what the conical thing. And this was based on NASA's experience on Mars. On the top, you have something, what you see at the bottom here on the top is something by which you can hold that. I'll show you how it was being held. And there's an antenna also built in there. And inside there's a battery there. And this all thing had to be done in titanium enclosure because very strong and lightweight. And then all the green thing, everything is sensor and communication electronics. So the conical part, the top part is basically to put it into the surface. And this was to actually then monitor thermal electric property. There was another design was there. Okay. All of this, because shorter time I'm not going to think, all of this was integrated into something that was going to be sitting on the rover, which would collect multiple samples. So there were different sampling cubes are there where you can capture samples and put it in those. And you could analyze them through X-ray spectrometer. You can do various things with this. All this was integrated into the sampling station. I'll just show you briefly. So these things all had to come within 5 kilograms. But you can see we are so particular about even a single gram, 396 and things like these, because each gram matters there. All of this was integrated into a payload deployment system which had a lot of flexibility. You see on the leftmost side, what you're seeing here, this is when it is traveling, it is stored. So it is very compact, it is sleeping in there. Then it could be in half height position and full height position. Half height, it will look at shorter distance, full height will longer distance. It could also be bent, so it could look down into the regular surface, and then it could also look at the sampling station here, the pink one. So all this flexibility was built into the system, so it had a lot of flexibility in that. That was a critical part of this design. Now this is how the thing looks like. Now, see, this is a sampling station here. This is that arm which is moving around. This is the X-ray spectrometer. The two cameras here. The cameras were also designed so when rover is moving, the cameras will be looking at the surface and giving the information. At the same time, what we had done was we had integrated two filters along with that. So you could, by adjusting the filter, you could get the images or video in different wavelength range, which gives you different information at any given time. And because of two of these, you get the stereoscopic images as well. Okay. Now, the way systems were going to work was that we were going to capture the image, send it to Earth. The sending to Earth was taking 40 minutes time because of low bandwidth. Then you send that thing to Earth, then somebody will give a command from here for the next motion. Okay. If this can be made intelligent, whole thing can be made intelligent, then it could take a lot of decisions there itself. Then the rover can move faster. And that's why the rover's movement was limited to only 10 meters in 24 hours, half of this. This is the core grinder which TC and team had designed. These are seismic sensors, 2 of them on this. One was on rover and one was on the lander, 4 of them. This is the thing, this was to actually go inside and hammer, collect volatiles on this one. This was connected by some kind of wire, and there was a, so that thing unrolls here inside this, and as it goes deeper in, for some reason if it gets stuck, there was a cutting mechanism, so you couldn't cut off, others get tethered, and you can't move the rover. So you sacrifice that part so the rover can move. So all that arrangement was given this, and there are a lot of other small things that were. So this whole thing was designed to be placed on rover, and all the experiments to be done on rover was to be done through this. You can see some examples of deployment. So this is picking up the seismic sensor node. It will lift up and hammer it into the surface. Both of these it can deploy like that. This is the rover. This is the solar panel. It could do 40 watts. Finally, when Chandrayaan 3 went, it had 50 watts of power. So that improved the thing. But this was 2010 I'm talking about. Actually, we went much later. This is the stored position. And this is when it's deployed. So it's looking down, and as I said, it could have multiple motions. The plan was to use different teams to develop different parts. Everything had to be integrated at one place. That was at my place. And I will not go into more details of these. Some of these was to be also procured from outside India, including. So I'll stop at this point because time we are running out. Yeah, I think we have run out of time, so I'll stop sharing here. Are there any questions? Yes, DC. Moon.
I think your instrument is enough for Mars.
Also for Mars, you can say, or
I think it's enough for Mars.
Enough for Mars as well.
Yeah, I think Moon isn't necessary. So many instruments.
That was the requirement that was given. And if you see LUPEX, most of these are there now. That was the requirement given by ISRO. And now with Dr. Sreekumar, we are rediscussing how to initiate all of this again.
But the mission is cancelled already.
Well, the 2010, when I made a this was handed over to ISRO, they had some discussion. I'll not go into details. And then it was, the Russian collaboration was still on. It was not cancelled in paper. So after the Russian collaboration was cancelled in paper in 2012, then ISRO approached me again. But then I was moving to Delhi in another position. They put 2-3 engineers with me, but they wanted all the designs to be done and given to them, which is not possible. So then I tried to reinitiate, and I remember that you had come to Bangalore once. I tried to get other institutes involved, but nothing happened. So most of this has not happened. So there's still a scope. In LUPEX, they're doing some parts, but it's very heavy instruments. These are much smaller in mass. Any other question? Dinesh, please. Yeah. Yeah, so if we can integrate intelligence into that, it will definitely help. So you can move faster and take decisions, and that's an important task. Yes. Throw it. Moon. No, it's not 0. It's 1/6 of Earth. So gravity is still there. It's only smaller than 1/6 of Earth. It's just like Earth. So if you jump on Earth, you'll jump less. On Moon, you'll jump more. Yeah, so just like projectile, it will follow the direction of the projectile. Yes, I understand what you're saying. So when it lands, after it lands on the moon, or wherever it lands, it had a mechanism to automatically align to gravity, because even antenna had to communicate. So I had shown some videos of that. Yeah, but once it lands, there was a self-alignment mechanism in that. It will align vertically. Antenna will open up. It has to communicate. So all that was built into that. Yeah, of course, it has to communicate. Any other question? Sasiji, we can stop then? Okay, so now I've been given the task to summarize. So, what you might have seen is that India got into the in situ exploration while the plan was there for more than 15 years. Only after Chandrayaan-3 landing successfully in 2023, it has taken a serious turn. Okay. The reason we wanted to host this event here was that we wanted to show that even within university, you could start working on such things. It need not be always that a research organization is doing this. In many countries, universities take lead role in these. And even if you have done nothing in this area, you can still start. What you see in the plethora of discussion that we have had, things like even moon villages have been created. Delhi, there was a lady who was architect. She was talking about how to create construction or where people will stay inside that is going to be important. Even psychologists have a role. Even lawyers have a role. So I met a lot of people on things. So you see, while we may think looks like a scientific thing or technology thing, I keep away, but actually it has opened up dimensions. Biological systems, everything becomes important. So purpose of this event was to actually make sure that we realize that within university thing, even if you are doing nothing, you're starting from zero, still you can contribute to this. And India is the right place right now to do this. Other thing you would notice in this area, in the space area, the international collaborations are very easy. Everyone is wanting to find why TC keeps coming here with a lot of excitement, because he wants his system to go. And he's not the only one, he's a little more excited. But I had gone to Jet Propulsion Lab in 2009. My host was working for 30 years. He said that, and I got a VIP welcome there. Because they want to see if they can get some system on Chandrayaan-2 through me. So everybody is looking for international collaboration in this area. And that's why you will see that in Delhi also we were there. All countries represented except US in large number, because US had a problem budget. So NASA was not represented well, which is surprising to think. But I think I would like to thank all the speakers also for coming here and for organizers for organizing. I think definitely this was a very high level discussion that we had. This could have happened anywhere in the world. So I thank all of you for joining this and hope that this will initiate some work within the country. Thank you. Sure, you are. This is important. You want.
All right. Thank you, everyone, for joining us today. We'll disperse now, and thanks to all of the speakers. Yes, thanks to all of the speakers who had joined online as well, and people who are offline. Thank you again.